Bilder set division cease, and be yourself a king of peace.
Before we start, I just want to make a quick introduction. First of all, I'm very happy to have you back. And in this chapter, we will be focusing on procedurally placing our modules. And since this chapter turned out to be quite big, it will be divided into 2 3-hour parts. And I will try to logically break it so we do not stop abruptly midway doing something. So when you get to the next volume, the numbering of the videos will be continuous. I think this volume will go up to part 4. Then we start at part 5 in volume 3. Oh, and one more thing before we start. In the last part, I forgot to mention, but better late than never, and that is, if you have any questions regarding the course or feedback, feel free to contact me. You can find me on Facebook or mail me, and I will be happy to hear you out. So, that's it. Let's start. Hello and welcome back. In this video, we're going to set up the basic attributes for our body that are going to be fed to the systems to set up all the modules. So, first of all, we will return to our roof base. And what I want to do is just to clean it up a bit. I just want to bring in attribute delete. And we're just going to delete a couple of attributes that are not going to be used by the system in the later stages. And so here we want to delete all the primitives, so all, except for we want to keep type and we want to keep sides. Side, I think it's called. Check. Yeah, so we have only those left. So let's go up and we will create a new subnet from the null node and we will call it body attributes. We'll connect it to the body. Oh yeah, our null is not connected. So let's call the null in. We would also need the roofs, so let's connect it to the roof as well. We'll call it in roofs. But from the roofs themselves, you only need the sides, so let's bring it last. And we will call it locate platform. And we say sides. Side equals to 1, and it's a primitive delete non-selected. Oh yeah, those are the sides. Then wait a second, we need to go back here. What we need to say is, when we have the extrusion going on, and we have this platform, we will have to make a new attribute. So attribute create. And the way we're going to sort the platforms is by roof ID. So, but we will say that it's -1. So, as if it doesn't have a roof ID. So, it's going to be a primitive, integer, yes. And we will call it here roof ID. That's all good. Go up and up and up again to our body. And here we want to say that roof ID is -1. Yes, awesome. And I see that we have an extra face, so let's spin the view and go back to our roof base, our roof extrusion. And then here we just want to say that in poly extrude we do not need the from this. Thank you very much. So up, up, up. We go into the body attributes and actually go up and color it right away in a lighter blue. Yep. So here are our platforms. We want to merge them together with our existing walls. For some reason we still have all these attributes. It's because we're not on this one. And we don't want to delete the roof ID. We need roof ID. Yes, thank you. So here we are. We want to fuse all the faces we have. And we want to bring in facet node. In facet node, before we do that, actually, as you can see, some of our faces are from the platform do not correspond to the division that we have in our body. So we need to make sure that it does. So let's bring the void node, not a convex but breaker. It's 2 by 2 by 3, and here we are. So that's why here we're gonna fuse, and then we're gonna say unique points, and we want to post compute normals. And now we wanted to keep only the walls, so let's say blast, and we'll also say keep walls only. And here we say that anything with a y normal that is not equal to 0 should be deleted. So it's a primitive, it's a point, and delete selected. So turn off everything. As you can see, we don't have any floors or roofs anymore. And the next step is we want to measure everything, because we need to know on which walls there are enough space to actually spawn a window. So let's measure that. We want to measure area. So after we've done that, let's make it a bit tidier. We want to create multiple things. We want to have windows, we want to have entrance door, and also we want to create a stair. So let's create a subnet for that. We call it stairs primitive. So out of all these primitives that we have here, some of them can be converted into a stairs primitive. So first of all, we want to isolate only the top floor, because if the stairs cannot be spawned on the ground floor, it just doesn't make sense. You don't need stairs then. So let's bring in blast. And I say it's called top floor only. And I want to delete all the points whose position in Y is 0. We will have some leftover points. That's why we will have to bring add node. And we will just say in polygons, remove unused points. Then we want to delete all the walls that are too small, because there are just simply not enough space for a door. So let's say if the area is smaller than 4.4, so primitives, then it is deleted, because this area is technically it's 2 by 3, so it's 6. We can even say less than 5. So delete small walls, we call it. So the next step is to find all the possible stair positions, for which you would need for each subnet, as we're going to access each face. So just say each primitive. We're going to say find all stairs points, extra s in the end, sorry. However, to be able to find those, we also would need roofs and body with the floors. So to this, we will need to grab the original in, and we will need to grab the roofs. So we say this is locate roofs. Actually, just let's grab the whole thing. So here we are, and we say that we merge them in here, this one and this one. So yeah, the whole body base, and we input it in our find all stairs points. So here, and let's unpin the view. Each primitive, yeah, we want the each primitive, yes. So here we have the primitive. So what do we do with it? So I'm gonna grab the null here. So the way we're gonna do it is we're gonna take this point and we're gonna compare whether there's anything in front of it and anything to the side. However, if we just keep the position as it is here, sometimes it will definitely intersect with the point that is here. So we want to offset it a bit and also make it a bit smaller to check with the roofs. So what we're going to do is we're going to poly expand it. We're going to expand on the inside so it's a bit smaller, and we're going to peak it. Oops, peak. By just a very tiny amount. And it's going to peak it in our normals direction. That's all good. So we're going to check in two directions. We're going to check in this direction, and we also need to check it to the side direction. So we need to create it vector. So point wrangle, and we will keep it, we will name it check direction for check. So yeah, direction for check. So in here we want to grab two directions. So we wanted to grab the direction of the, actually let's make it bigger. Oops. So you can see, so yeah, we need to grab two directions. So direction 1 will be our current point position minus point of its neighbor, so ptnum plus 1, and we want to modular it on endpoints from 0. So if it is like a point number 4, then the next point is 0, not 5, because there is no point 5. So, and the same we want to do, but with a neighbor that is smaller by 1. So let me just actually copy this line, paste it here. So minus 1. And what I want to show you is if we say that our normal is direction 1, so you can see, so every point's direction is continuing the edge. And the same will happen if I say it's direction 2, it just will continue the other edge. So what we want to say is our normal should be additive of those two, so direction 1 plus direction 2. And then we get bisectrix of the angle. However, we do not need the bisectrix, we just want a 45-degree angle, so we're going to normalize it, and we're going to round it, and it will give us a 45-degree angle, because once we normalized it and rounded it, it should give us 1 and 1. So yeah, here we go. And that is the direction that we need to check. So if something intersects with this face in this direction, then we cannot point the stairs there, because our stairs are going to be placed under this angle. However, we do not want to override our normal that already exists, so we're just going to create a new one. We will call it N2. So yes. We would also need to create an attribute to hold primitive data. So right now, just make it a 0. It does not matter, because in this point data, we're going to store as a primitive number. And we need to store the primitive number because as the outcome, we're going to have only the point, but we need the primitive itself. So we're going to grab it from outside of the loop. So we need the primitive attribute for that. And the next step is to, wrangle node. The next step is to check whether this primitive, I mean its points, can be indeed a driver for our stairs. So find stairs. And we're going to run from a primitive. So again, we want to grab the points. Here in ptnum. We want to grab the original normal. So we say that it's normal is 0.0 and technically it should be any point, so 0. As well, we will have a vector normal too. However, it is different for every point, so that is why we're not going to identify it right now. We would also need all the PV, UV for our intersection check. So in for each, where we're going to check every point. PTS. We will need to know the position of the point. So let's grab the position vector. Position equals to our point. Position attribute from our P. And now we can identify normal too. It's a 0.0 and 2 from the P, because every single one has different values. And now we say that if the position of this point is 3, because we only want the bottom points, we don't want the stairs to spawn on the top part of the wall, then we need to check for 2 intersections. And let me make integers for that. We'll call it intersection front and intersection side. So those 2 intersections we would need to check. So intersection front is intersect function with the first index input from the position in our with our normal. However, we do not just need the normal. So let me create a new vector here. We call it direction front. Because if we're only going to check what's in front of us, that is not accounting for what is below. Because we also need to account on what is below. So that is why we just need to say that normal plus 0, minus 0, minus 1, and 0. And here we want to say that we want this direction in front and multiplied by 100, so it just goes not infinitely, but quite far to check for the intersection, and then PV, UV. So apply. We want to check intersection side, and on the side we already account for the bottom direction as well, so there is no need to make the new vector and subtract anything from it. So also from position, and it's our normal 2, also multiplied by 100. Then PV, UVV, using the same ones because we do not need to know where the intersection happens, doesn't matter. And we say if intersection front is false, so nothing intersects with front, then we check for the side. If inside is also nothing intersects with it, we're like, yay, that's what we want. So we create a new point, and for that let me create the variable, so new point. So we create a new point. We add it to the same position that we're checking, and we set it attributes. We set point attribute 0. We set same normal, so new point, and its normal is not the same one as the initial point. We want to set it to normal 2. Set, because this normal will contain where our stairs, in what direction our stairs are placed. So in the fact that this direction is much more important than to know the normal. And we also want to point attribute 0, and we want to also tell it what primitive number it is. It is from the checked primitive. Sets, and what is checked primitive? Let me identify that. So in the very beginning, integer checked prim is a channel, integer channel of a stem. Oops. So apply. So in here, let's comment everything. So check every, actually not here, let's grab it here, yeah. Check every point and its intersection with the geometry from input of index 1. Check both side and front intersections, and if neither are true, then it is the point we need. Apply, accept. So yeah, and I forgot to make one last step. We do not want the primitive. We want to remove it. We say from the from the 0 index, 0 primitive, remove with the points because we don't need the points. So I'll apply accept. So here, as you can see, two possible options. It can go either here or here, and both are valid. So once we check every single thing, let me show you. You see how many possibilities we have. Let me show you with this one. And for example, here, there is no point because if we would put one here, it would intersect with our other walls and roofs. So we have a lot of them, and we just need to pick one. So what we're gonna do, after we found all of them, we want to bring a wrangle again. We will call it pick stairs point. And yeah, run over points. So as you remember, we misplaced the points a bit, so we need to snap them back to their positions. It's easily done just around their position. So apply, and as you can see, they are snapped back to the grid we had. And in here, we just need a couple of things. We need the seed, obviously, because it's going to be a random pick. So seed, and we will create a random number, which is random of our seed. We also need to fit it from its original values to the maximum point number. So in points, -1. And we need the integer out of it. So round it and convert it to the integer. So once we have this random number created, we say that if the point number is not the same as the random number, just delete it. So remove point 0 platinum. apply. And we also want to have a possibility of the stairs, so we don't want them to be all the time. Probability, and let's call it prob, apply. And we just say that if probability is bigger than random of the seed plus the point number, then we will remove it. We create spare parameters, and our probability is 0, so okay, that's actually smaller. Yes, and the seed is awesome. Why are we keeping all the points? Let me check 1 second. And yeah, if our probability is not, then we also need to say that this, yeah, apply. Yeah, amazing. So here we're only picking 1 out of all the possible points. So now we also need the face. So we need to bring in blast. We're gonna call it locate stairs prim, and we're gonna say that delete this point from big stairs 0. It's called prim 0. It's primitive, and we want delete non-selected, so there it is. Actually, that is not the one we want. Oh yeah, I forgot to put the stamp here, so it's always 0. Sorry. So going back inside the subnet, click here and create a stamp. So stamp for value and 0. Go up. Now it should be correct one. Yes, this is the correct one. Awesome. And we also want to switch between null and locate, because if there is no points in pick stairs primitives, then we do not need to blast anything. We just need to select nothing. That's basically pick. So if it is 0, which in this case is not good, we merge all of this together. So yeah, here it is. This is our driver geometry, so to say. So we have our stairs primitive with a point, and this point shows us the direction where the stairs is going down. So the next step is to check for windows. So we need to know where our window is going to be located. So let's bring color and just set it to white. This is purely for us for visualization purposes. So let's bring in a new wrangle. We're gonna call check for no windows. So right now we're gonna just determine faces where it is never possible to have windows. So if you look at the, let me show you, yeah, like this. So in certain cases, like for example here, like this wall, it is abstracted by the roof. Like there is no sense why anyone would build a window there, because you would always stare at the roof. So in this kind of cases, and here as well, we want to make sure that no windows are spawned, because it just doesn't make any sense. So that is why we're going to check for no windows. We would need to bring in the roofs. So we only need the roofs themselves. We don't need the platforms. So delete non-selected, and we will call it locate roofs. And we will plug it right here into the second input. And we would also need our stairs point. So blast. So if I'm not mistaken, it's gonna be the last point. So let's make it the first point just by switching the order here. So let's go up, and here is our point. Let's call it stairs point. And the reason we need this is that, well, not in this case. Actually, let me make a case so we can see how it works. me change the seed to something. No. Yeah, this one. Perfect. So this one, it will, like, if we have stairs here that go down, that means that this primitive cannot have windows, because no one would make a window and then obstruct it with the stairs, or on the contrary, first make the stairs and then make a window that doesn't have any purpose of having a good view or any light. So that will also be a constraint for our no windows wrangle node. So we will bring it into the third input. So to make it easier, the navigation, let's color certain things. This one as well, color. Okay, and here let's bring it bigger. We want to run it over primitives. And let's start. So again, we want to bring in all the points from our primitive. So prim points, 0 primnum. We will check for intersection, so we will need our favorite PV and UV. We will need the variable to hold the intersection, so intersect. And we're going to check from the center of the primitive. So let's say find the center of the primitive. So that's we're going to check for the intersection. And if, for example, the center of this primitive intersects with the roof, then we will say don't build the window. But if it doesn't, then yeah, build it. So find the center of the primitive, yes, and for that we will need to create a vector, which we will call origin, and it's a 0, 0, 0. We need it as a starter, so to say, where we're gonna add all the positions. So let me show you how it's done. I think we already did it actually previously in our series, but we just add to the origin the point position. Oops. Oopsie doopsie. So P and our PT. But we don't want just the center. We want to make it a bit lower, because sometimes I saw it in the already in the later stages when I was making the system, that if you have it on just from the center, it can still be kind of half obstructed, so to say. Like the roof is, the window is still kind of like, I wouldn't build it there. Personally, I would be like, why? So I decided just to lower the center. So let's do it. Lower the center point to check against. So I would just say that origin is set origin.x divided by 4. Origin.y. Everything is divided by 4 because we have 4 points. Don't forget that. And here we're lowering it by 0.25. And we also say origin.z divided by 4. This is actually kind of a long way to write it, so let me rewrite it differently. Actually, it will be much faster if I just write it like this. Origin divided by 4 plus 0 minus 0.25, 0. Yeah, better. So the next step is you want to find whether these points intersect with the roof. So let's name it find whether the point intersects with the roof. So we want to grab the normal because we're going to check against the normal. So point, an attribute from our, actually like our first point of the points array, because all of them have the same normal. And our intersect, we can finally identify it. We said that this is an intersect function. We check it with the first index input from the origin position with normal, and we just multiply it by, let's say 2. Don't make a very big number, because sometimes if you make it too big, it might not intersect with the roof that is in front of it, but there might be more roofs further away from it. So make sure that you just have it normal multiplied by 2, because that means this checks as far as one tile. Because if you check more, there might be roofs that kind of obstruct that ray, but they do not actually obstruct the window itself, if it makes sense. So make sure not to make it too big. And now, here's the part of how we're going to check for the stairs. So let me apply and accept that. Whenever we have stairs point, we want to check for this primitive whether its top and only top points touch with the stairs. If they do, we will mark it as a primitive that shouldn't have any windows. So let's do that. Let's comment to find whether the top points touch the stair point. So let's do that. So we want to grab positions of our top points, and top points they are 0 index and 3rd index, and that is true by default unless you change it. I think you can change it. So after you grab those, we want to run 2 point clouds. So p cloud 1, we want to open it in our 2nd input index. We want to check for position from our position 1, small radius, and we only want to find 1. And then we say again int p cloud 2 pc open to p position 2 0.1 1. Then we will create an integer that's gonna count how many point clouds return something. So if pcnum found of our p cloud 1 plus pcnum found p cloud 2. So if found is bigger than 0, so either pc found of p cloud 1 or p cloud 2 had something in it, we say that we want to check. Let's say it. Let me apply. I need to show it to you. We want to check whether the normal of the stairs and then the normal of the face that we have are perpendicular to each other, like the planes that they create. Because, for example, this primitive, it also has the stairs point on its top points. However, we still want a window there because the point normal and the stairs normal are going into the opposite directions rather than in perpendicular ones. So we want to check for that, and to do that, we will say that we need to grab the stairs vector, stairs, and we say that it's a normalized version of our point of the 2nd index input n and 1st point. And we want to say that if normal.x multiplied by stairs normal x.x plus normal.z multiplied by stairs stair and .z is not equals to 0, so they do not cancel each other out, then found is 0.
Hi there! This is a post recording, that is why the sound may be a bit different as I'm using a new microphone. I was rewatching the content before the release, and I decided to add these additional explanations where I think they would benefit you. You will see more of them later on, and there I will skip right to the explanation. So, here we have 2 normals, and the way we are identifying that they're perpendicular, and please note, it works only in our grid-constrained environment, is that we are looking at their values, and if one of them has a value in x-axis, it cannot have a value in z, which means that if you want to have a perpendicular, the only direction it can go is z, knowing that if we multiply their x and z values and we get a 0, that means that they're not parallel. And since they can only follow the grid here, we have our perpendicular.
So in here, we want to say that if the intersection is true, or the stairs are in the way, let's put it this way, make the face gray for visibility. So say if our intersect is true, something intersected, or our stairs were found, we say that it's a type wall. This is a new attribute we're going to create. It's a string one. It's going to be very important. It's going to drive other parts of our system. And we're just going to make a quick for each loop. Just want to make gray wall. So set point attribute in 0 index. As D stands for color.
and we want to modify p, and we want to make it just gray, not 0.5, comma 0.5, yes, and we want to set it. Apply, and there is an unexpected identifier. Point attribute. Oh yeah, I see. It's a point instead of a comma. Apply. Accept. So now, as you can see, some of our walls became gray. So this one's became gray because there are roofs, and this one became gray because there is stairs. But note that this one didn't become gray because the normal of the face goes in the same or opposite direction of the stairs normal. If we judge it in Z and X plane, not in Y. So the next step is to assign our windows attribute, for which we will bring another attribute wrinkle. And technically all the wrinkles we're going to create now, you can merge into one, but I'm going to do it in separate steps just so it is easier for you to follow. So this one will be assign window attribute. Again, we want to run it over primitives. And we will need a seed again. So channel seed. We will need the points. So prim points 0 prim num. Another thing we will want to add is a probability of our windows to spawn. So float prob channel probability, yeah. And we want to make it a bit custom, not just checking the probability, but we also want to make sure that if the prim is on the top floor, it has a higher chance of having a window. And for that we will need to add a new variable float. We will call it add, and for now it will be 0. And we say that f point position from the 0 index input of the first point of our array and y of that position is bigger than 3. Then we want to add 0.2. And we say that if type is not a wall, because if it is a wall, we cannot make a window there, as well as we want to request our area to be bigger than 3. So if those two conditions are satisfied, we want to say that if random of the seed plus our primitive number, prim num, is bigger than our probability plus the add, then the type is wall. I mean window. Oh, wall. Sorry, wall. It's a wall. So else, it's a window. Window. I want to say that for each we will color it. Int p in our PTS. We want to color it, and we want to make it a very nice yellowish color. So SD for color, our p, and we want to say 1, 1 and 0.2. And don't forget to set. So apply, accept. Okay, some problems. Unexpected on the 11. Oh yeah, I missed semicolon here. Apply, accept. So right now nothing is windows because our probability is 0. Let's make a probability higher. And some of those are not satisfied. So let's see type. Oh, for some reason all of them are walls. Let me see. Type wall. Okay, so if we say the type is nothing in the beginning, apply. Yes, okay. The problem was that here when we say that the type is wall, it thinks that wall is a default, so it makes everything wall. Just make sure in the beginning to say that the type, I will do it at the very beginning, is nothing. The default type of variable when we just, attribute when we just create it, it's nothing. So here you go.
And that is our windows, the yellow ones. And note that we never get window on this primitive, because it's just too small, as well as this ones, the platforms. But if they are big enough, there can be window as well. So the next step is we want to assign the door, and not just any door we will be assigning, and this one we'll be assigning the stairs door, because stairs have to lead somewhere, so they will lead to a door. So we say assign stairs door. Our primitives again, and for this one we will need the stairs primitive to the second input. Let's make it bigger. Again, we will need the points, so prim points, and from the 0 index, prim num. We will need a p-cloud. We're going to check it with p-cloud. We will need a position, which we're going to access, as well as we need to found equals 0 for now. So let's grab a for each loop, and for every point we're going to grab its position, and we want to find that particular primitive, the stairs primitive. We want to find it. So our p-cloud is pc open, 1 p from the position, and if something was found of that p-cloud, then our found is ++. And the thing is, we need our found to be equal to 4, because it means that every point in the primitive found a point of the stairs primitive, which means that they overlap. So we need to say found equals 4. Then we need to say that s type equals door. Door. And for each in our points, we will make a nice blue color, set point attribute, yes, 0 SD P and blue RGB, so blue, okay, 0.5 and 1, set, apply. And a misspell somewhere, ambiguous call, float int 21. PTS. Oh yeah, I forgot to mention that it's an array. Apply, accept, all good. So here we are. It is our blue door primitive. So in a very similar fashion, we're going to assign the entrance door. So grab a new wrangle. We're going to call it assign entrance door. And again, run over primitives, make it a big one. So here we'll need a seed again. So float channel seed. We will need to create a list to hold all the primitives that are on the bottom floor, which reminds me it has to be a detail, not a primitive. So next step, we will need to grab the points. So actually, I'll put it in the same line. So we will need a points array. We will need a vector position. And let's comment that pick the prims that are only on the ground floor. Because we don't want our entrance door to be on the top floor, that wouldn't make any sense. So we want to access all of our primitives. PR equals 0, PR is smaller than all the primitives in the 0 index input, and bigger by 1 step with every loop iteration. So another thing we will have to access is its type, because if it's already a window or it's already a wall, then we don't need it. So we will need to say string, and we will call it type, and we will say the type equals to prim 0. We need to grab the type from our PR. The points are prim points of the PR, and the position, we just need to grab one of the bottom points. So let's grab the index 1, and we say that if position.y is smaller than 3 and attribute is not equal to wall, however
it's fine, we can override the windows, but just make sure it's not a wall. We're gonna say that append this list to the list. This primitive will be appended to the list. So, and we say in the list of picked primitives, choose a random one. So we will create a random number that was random from seed, and we want to feed it from its original values of 0 and 1, from 0 to the length of the list, so prim list minus 1. And then we want to say that we want to round it because we need the integer, and we want to convert it to the integer right away. One more bracket, apply, attribute, unidentified variable attribute, 13. Oops, sorry. Type, not attribute, type. Apply, accept. Oops. Get back. So now we want to set this random primitive from the list. We want to set its attribute to be a door. So we say type from prim list, random number should be the door. Door and set. And when you need a new array, PTS2, we're going to grab the points of the selected primitive. So prim list random number. And all those points, just color points visibility for each. We're going to color them again in our nice blue color. Set point attribute, SD for color, our P, and what were the numbers? 0.2, I think, 0.5, and 1. I think that's the one we used. So apply accept. Yes, that's the one we used. So let me bring the seed, and let's see. Yeah. And it notes that it never overrides the gray primitives. So one of the last steps is we want to make sure that we bring another wrangle. It's going to be a very short one. We just call it connect type because now if you look in our spreadsheet and you look at the type, some of our primitives still don't have any type assigned. So that's when we want to say that those have walls. So if we say if as type is roof, so those are the platforms that we were brought into here, or it's not anything. It's just like emptiness. We want to say that then it's a wall. Apply, accept. So now, yeah, we have walls, window, window, 2 doors. Awesome. So now what we want to do is we want to merge everything together. We want to group our points so we can always find it. We will call it stairs point. It's just a point. Stairs PT group, and we just want to merge them together. So here's our foundation with the body attributes that we're going to be used to place the modules. And in the next video, we're going to place our very first modules, which are going to be supports. So I'll see you then. Hello and welcome back. In this video, we're going to place our very first modules. So let's start by creating a null, which we're going to collapse into a subnet. And our first modules are going to be supports. So support. For the support, we will need to take the body base, because our body base contains the floors which we already assigned certain values. If you remember previously, we now have a support partial and support full. So those will be the drivers for our support system. So let's go inside, connect it to the null. Our supports can be of 2 types. It can be a full support or a partial support. So we will first start with a full one. So let's bring in blast. and we will say locate full. And we say that if type is support full, then we want to keep it primitives. So that is the only primitive we have currently, but sometimes there are cases where there can be multiple ones. So to identify how many of the supports we actually have, we will need to fuse and divide. And in divide, we want to say that we want to remove shared edges. So let me see if I can find a case that is a good example for what I mean. Okay, if you put in the seed 126 and you go to the support, you see that we have 3 primitives. However, those are only 2 full supports. So if you look in the mesh itself, it should be identified as 1 support and 2nd support. That is why when we locate it, we fuse it and we divide it. So we get rid of this edge here. Therefore, it's treated as 1 primitive, and that is the count that we're going to use for our for each loop, which we will call get pivot points. And why pivot points? Because that is going to be the driver. Those primitives will be the driver for finding our pivots, because that will be the main technique that we're going to use to place modules, because the support modules are already pre-made. So the only thing that we need to find out is the allocation and the rotation of our modules. So let me go back to our initial seed of 2.48, I think it was. 2.48. Yep. And here we will connect it to the first input of our for each loop. And we will say that we want each number, and we want it to run as many times as we have primitives in our first input. So op input path index number 0 and -1. So currently it's going to run only once. So let's dive inside. Here we will have to locate. So blast, that you want to locate this primitive. So stamp up for value 0. Don't forget the brackets. And group type is primitives, delete non-selected. So the next step, we will need to find 3 pieces of our modules. Those will be the column, the arc, and the fence. So those will be broken into 3 separate parts, and each part will be controlled with a seed. Therefore, we will need 1 global seed, so it's just easier for us to manage. So let's call it seed, and let's color it to our red-pink color. And let's start with columns. So I'll just create null, call it in, collapse it, and those will be our columns. So column. So let me illustrate what we are about to do. Let's imagine that this is our house and this is our support primitive. So if we divide it according to our grid, we will get something like this, where every big point is a column. However, we do not want this as our columns. So how do we identify those points? Because we do not want the columns to obstruct the walls. So let me grab a different color. It's like orange. So first of all, we will need to identify those walls. So, so these are the walls that are touching the support primitive. Based on those, we will mark the points that belong to the walls. So let's grab another color, like green, and let's make it like 40. So this point, this point, this point, this, and this, they belong to the walls that touch
the support primitive. However, we do not need to delete the end ones. We only need to delete the ones that have both of its neighbors marked as green. So that will be the main identifier. We will look at the point neighbors and we say, okay, so if I'm checking this point, I'm checking this point, and I'm looking at the two neighbors and I'm saying, okay, are both of its neighbors marked green? If no, keep it. If yes, delete it. And then if we look at this one, both of its neighbors are marked green, so this point is to be deleted. So we say, yeah, this point is bad. So is this one, so is this one, and we do not need them. So let's implement it inside of Houdini. To illustrate the mentioned case better, I choose the seed of 131 because it has support consisting of 3 primitives that form a corner. So with this one, it will be easier to illustrate what is going on. So let's go back into the support subnet and to the get pivots and into the column. So as I mentioned in the illustration in Photoshop, we will need to know where walls are, and for that we will need to bring in the body. So let's bring, so there's a body base, yes, it's already in. Then we need to call this now in, and we will need also to bring it into the for each subnet. So here we will need to bring it into the columns. And the first thing we will do, we'll bring an attribute triangle where we will assign the initial values. So we will call it init attrib. And we will, first of all, we need to rest the primitive on 0, because this is the way we're going to check it with the walls. So let's say p.y is 0. And we will also create a new attribute called name. This is the name of our module, and it's a column. Column, yes. So the next step is to find those walls. So let's bring in our body. We will call it in body. From that we will only need the walls, so let's locate walls. Let's call it locate walls. And we need to say that the normal of the point is not equals to 0. Delete non-selected primitives. Oops, points. And delete selected. So yeah, that is all of our walls, because we do not need to check the floors. So let's bring another wrangle node. Here we will connect to the first input, we will connect the walls. To the second input, we will connect the support primitive. And we will call it keep touching walls. So it will be running all primitives. Let's bring it bigger, Alt-E. So for every wall, we will be checking its points, and we need to find, based on those points, the points of the support primitive. So let's bring PTS. We will grab prim points of the current primitive we're checking in our input index 0. We will, for each of those points, we will be checking position. So we will need to grab that. So let's create a variable for that, vector position. And position we'll grab from the point we are checking in the for each loop. So pt, and we will need to create integer to hold our point cloud, because we're going to check everything with point cloud. So pcloud, and let's say pcloud is equals to pc open. We're going to check the index number 1, check position. From our position, small radius, and we just need to find at least 1. And if we did find something, we say that we need to store it into another variable. So let's create another variable, integer found, which is 0, starts with 0 for every primitive. And we say that if something was found, pc_num found, in our pcloud, then our found is bigger by 1. So how many times does the wall need to find a point of the support primitive? Well, it has to find it twice, because that means that it touches in both points. If it touches only in one, that means they're not actually connected directly. So we say that if found is smaller than 2, then we don't need that primitive. So we say remove primitive, the one we are checking now, and yes, delete the points of the primitive as well. So apply. Let's see if it worked. Yes, it did work. And let's comment it out. Let's say for each point, check whether it touches the support primitive. And if the primitive has at least 2 points that touch the support primitive, we keep it. Apply. So as you can see, those are the walls that touch our support primitive. So the next step is to mark the points. So let's bring another wrangle. This time the first input will be the support primitive, and the second input will be the walls we just identified. And we will call it mark points, and deriving from the name, it will be running over points. So let's bring it bigger. So what do you want? You want to find all the points that are on the same position as the walls. So for that we will need a point cloud again, and we will run over index number 1 from the position and the position of the current point, small radius, and we can find as many as we'd like. It literally doesn't matter, because if at least you find 1. So if at least PC num found of our p cloud is bigger than 0, so if at least 1, we say that it is marked. So we'll create a new attribute called marked, and fi. There. So apply and accept. So to make it a bit more visual, I will just create a color attribute for you, and I will mark them black. So as you can see, the points that are touching the walls are now black. So what we want now is to bring a poly expand. We only want it to go inside. We want it to be 0.12. I found it works the best. The reason for that is because our column has thickness, and if we place it exactly on the corner of our primitive, it will look a bit odd because it will be sticking out of the building, so it kind of needs to go a bit inside, and poly expand is a perfect node to do that. And only after the poly expand we can now bring another wrangle where we delete the non-needed points, because if we do it before, we can't use poly expand. So bring it again, and we will call it delete points. Again, to run over the points. So here we will need to grab neighbors with the neighbors function of the current point. We will need to hold the marked attribute. We'll also need to know how many were marked of the neighbors that we have. So let's run into the neighbors. Let's say that int so inside we will grab the marked attribute. So point 0 marked of our neighbor. So if it is marked, so if marked is 1, we say that marked count is bigger by 1. So let's comment, let's see how many neighbors were marked by the previous wrangle. So if the point is marked and its neighbors are also marked, delete it. So that's what we're gonna do. So we say if the point itself is marked and its neighbors, marked count are also marked, think there is a misspelled here. Marked, yeah. Then we want to remove the point. So remove point, current point we're checking, ptnum. So apply. Note has a warning, a marked count. Oh yeah, we forgot to identify marked count is 0. So yeah, as you can see, we deleted this corner point because we don't need it. We only have the end ones of the wall. So now the next step is to apply the correct normal for our placement. So I will bring another wrangle. We will call it rotation scale attributes because we will also handle scale in this one. Let's bring it a bit bigger. And for this one, we will need a seed. So we say float seed is channel seed because our rotation will be random. Since our column has 4 sides, we will make a random rotation of 90 degrees in from 0 to 360. So what we want to say is that the normal in X is a round of the random of the point number, because for every point it will be different, plus seed. And at random we will multiply by 2 and subtract 1. This way our random is random between -1 and 1. And we say that if by any chance our random is 0, so our X became 0, you want to make sure that the z-axis then gets some kind of value. So we say that n.z. And we repeat the same thing, but we change the seed value. So we say that it's another number. So apply, and the y is 0, and the scale is 1. So apply, accept, and as you can see, we have a random rotation. So let me, I guess it will be more visible if I delete the primitive. Delete geometry but keep points here. We have random rotations in 4 axes. So let's go up. So from the column, we will need to grab the seed. Oh, we even forgot to delete it, to create it. So let's grab the float here. We'll call it support seed, and it's seed, apply, accept. To this seed, we will definitely need to link it to our global one. So let's bring the global seed, yep, here, and paste relative reference. And it also is different for every iteration. So we also need to bring the stamp into this one. Oops, did I copy something else? Copy plus. Yeah, that's correct. And then this seed, we also need to copy parameter, and we will need to bring it inside of our rotation and scale. So here we need to create the parameter, and we will just paste relative reference. Very tidy and clean. So now let's go up. We will not need the marked attribute anymore, so let's clean it up right away. So we won't need the marked primitive attribute detail vertex point. It was a point, so we don't need the marked one. So we will call del attributes. And now we need to go up again. Actually, we can let's take out the delete attribute node, and we will do it outside of the loop, so it doesn't do it every time. So we will only do it once here. And now, once we have the support, we can finally place the modules, our very first module of a column. So let's create a for subnet for that. And we will call it place modules. We'll need to make it each number from 0 to number of points from the first input, which we're going to connect in a second. We'll need to connect this. And we will need to locate the points every time. So locate point stamp, go up for value 0, the brackets, and delete not selected. So every time I will have the point. So the point, if we go inside of it, we created a name attribute. It is a column. We will also need to inherit the parameter, or it is a support. So right in the beginning, we will write a new wrangle. It is called, actually right after we locate the full, we will call it inherit attributes. So for every point, we say that find its primitives, all the primitives, so point prims of the current point, and its type is a primitive 0 type of the first primitive. So if you go now to spreadsheet and we go to type, it's all support full now. As well as we also need to know its folder, and in this case it's just a support. So why do we need the type and folder? Because when we're going to bring in a lot of modules, we don't want to every time manually say which module it is. We want to, it's important to store all the information needed. So let me illustrate you. Let's bring in the file node. And we will say that, so if you just go to heaps, that's what you have to, that's what you will see. And I attached the modules folder for you, where all the modules are already made, so you can use those or create your own ones if you want. In these modules, we will write where to go. Like, we don't want to every time to manually select a folder and manually selecting an OBJ. We want to make it procedural, so to say. So we want it to be read from the points attribute. So let's accept right now. And now we will write an expression here. So we will say that it needs to be read from the point. So bracket, which means it's going to be a string. So it's a points from locate. From the first point there, we want to grab the folder attribute. Then we want to grab the type attribute. It's also from locate 0. We also want to grab the type attribute. And then we want to grab, am I doing it correct here? Something's wrong. Oh yeah, I forgot to close this one. And points, we want to grab the name. So locate 0 name. And then we also want to grab, let me do it like this. Let's just copy this. And also we want to grab the variation, which we haven't created yet, but we will in a second. So variation. So apply, accept. So it will complain now because we don't have any variation attributes. So let's create one. We will just create a dummy now, right? So attribute wrangle var attribute for every point. The I variation, it's actually a string, sorry, string variation equals 0, 1. Still complains. Yeah, it says it's unable to read the file. Let me see. Oh yeah, and don't forget to say that it is an obj.obj apply. So right now, if I go F, we are getting a column because of our point. Our point is here and our column is all over there, so we need to place it correctly. So we'll just use a copy node for that. So let's go up, and for every point we need to get, okay, getting something weird, spelling error here.
So right now, for some reason, it doesn't delete this one, though it was deleting it a second ago. So let me check it again. Oh yeah. Oops, it has to be the in one. So yeah, that was a mistake. So yeah, now it's all correct. We are getting that, yeah. Oh, good. So make sure that in is connected to the for each subnet and not the inherit attributes. That was my mistake. So yeah, as you can see, our columns are nicely placed, and we don't have the ones that have both neighbors touching the walls, so they all end on the walls. So the next step will be to place the fence and the arcs, which is quite simple because now we have the foundation for them, which is our columns, and we will kind of utilize them all the time. So we will need to dive back into the get pivots, and we will need to create a new subnet.
So in the next video, we will be placing the rest of the full support set, which are fences and arcs. And I see you then. So for the next step, we will find the pivot points for the arcs. And for that, we will need a new subnet to keep it tidy. So let's create a null. Let's connect it. Call it in. And collapsed into subnet, which we will call arcs. Arc. And inside the subnet, first of all, we need to sort the points. We'll sort them by vertex attribute, by sort by VTX. So points by vertex order, yes. And now we will add a scale attribute as well as a normals. So let's bring a wrangle attribute. So for the arcs, like if you load my arc module, which I provided you with, it supports arc. You can see that its pivot is located on the bottom right. So we need to make sure that the pivot of Z always points in the correct direction because it will be as a driver of the orientation. Also note that I put it on the top. I wanted to make it so because then the pivots for the arc, and the pivot for the fence would be the same. So if you merge them, if I place them together, they already have the correct positioning. So that is the reason why my arc is kind of floating above the ground. This was just done for the convenience and just to speed things up. However, if you want, you can also place it on the bottom and make the height procedural also possible. There is no limitations whatsoever. So let's get back to our points. So right now the normals are incorrect. They're putting in all kind of directions, which we don't need. So let's bring it bigger and let's start. So first of all, we need to know the total number of points, because the way we're going to drive the normals is every normal will point to the next point. For that, we will need to know total point with endpoints function. We can write from the index 0, or you can also write geoself. I prefer to write just the input number. We will also need to know the neighbor point. So for that, we will say that it's a point number current -1, and it's +1, sorry, and it's a modular of total PT. And then we can find the vector. So we say that neighboring position is point 0, P, and of our neighbor point. And then we find the vector normal, which, as you remember, is just a subtraction of the two positions. So neighboring post minus current position. So we say that normal is equal to our found normal vector. So apply. And as you can see, it always points to the next neighbor. Every normal. That's exactly what we need. We also need to write the scale. So float scale is the length of our normal divided by 2.
Why by 2? Because our module is already created with bearing in mind that our module grid is 2. So it is already by default 2. So scale of 1 means that it's 1 in the module tile, but module tile is already 2. So we just need to divide it by the module tile. So the scale is done. Let's rename our node. We call it wrangle scale and normal attribute. Then we'll bring the new wrangle node, which we will call delete longest edge. Because in many cases we are going to have things like this when we have like one very long edge, which we don't need because previously a point was deleted from there. For each point, we just need to know that if the length of its normal is bigger than 2.1, that means it's off the grid. Then we don't need that point, so remove point, 0 and the current point. Apply, accept. And it has a warning of, oh, yeah, missed this here. Yeah. Oh, good. Yeah. And actually, we don't need a separate wrangle for this, so I'm sorry. We can just put it in here, so we just have more space. So we just say delete edges of the grid. Here we will call this find normal, and here find scale based on the grid tile. Apply, accept, and oh, the final important thing is that we want to assign it a name, like we did previously for the column, but in this case, so assign a name. The name is R. So apply and accept. So let's actually call it init attributes, since we have a lot of attributes in here. So initialize the attributes. And then we want to check with the touching walls as well, like we did previously, because sometimes we can have only like one grid tile support primitive, and the columns exist on each point. However, we do not want the fence touching the wall. Therefore, we need to check for that. So we will create an object merge. We'll bring the touching walls that we found earlier. So we will just go up and we will go into the column, and we want to keep touching walls, accept. So that is our walls. We brought them back. And we want to pick them since we used poly expand, and to make sure that they are on the same places. So 0.12 should be enough. And we need to bring in a wrangle node, attribute wrangle, connect to the first input our support primitive, and to the second one touching walls. We'll call it check for walls. And here we want to check for every point, we want to bring in point cloud. And in this point cloud, from every point, we're going to check, is this point lying on the wall? So we say that PC open, first index from our point position, 0.25 should be enough, only one. And we say that if PC num found of pcloud is not equals to 0, then we have a we need to make another check. So how do we check? So let's say that we have a point here which has a normal along here. So how do we check whether all this normal lies on the wall? Well, we'll first check this point and we ask, does it lie on the wall? We say, yes, it does. So now we need to move this point. Well, we don't technically move it, but we will check a new position that will be from this point along its vector. And if that position also touches the wall, then it means all the vector lies on the wall, all the normal, and we need to delete that point. So let's implement that. We'll say vector new position. It's a normalized normal multiplied by 2, this is our grid size, plus our p. And we will create a new point cloud, pcloud2. And we're just going to do absolutely the same, but we're going to use a new position to check from. And if this point cloud, so PC num found, also found a wall point, so it also lies on the wall point, then we have a problem. Then we say remove point. 0 point number. So apply. Okay, we have a spelling error somewhere, I guess. Syntax error, unexpected if. Oh yeah, forgot semicolon here. Apply. Identified variable handle 2. Oops. Handle point cloud 2. Sorry about that. So yeah, apply accept. So as you can see, this point number 4, though it is close to the wall and technically lies on the wall, it is not deleted because when we checked it again, its normal end position is here and it definitely doesn't touch the wall. So that's why this was kept. So yeah, that's it for the arcs. So let's go up. And the last step is we want to have them. So first of all, we want to merge them. No, don't disable it. Merge it. Yes, let's check if it works. Okay, works beautifully, except for one part which we haven't accounted for, is the scaling. So let's actually go inside of our place modules, and we say that we want the transform node. We will call it scale. And it's a scale in Z, and we want to grab point, locate, and to grab the scale attribute. So scale 0. So now, if I go up, all the sub-arcs are nicely scaled. Because as you remember, we accounted for the normal length. So we actually know exactly the length from here to here. And we know it perfectly fine. We know exactly how long our arc has to be. And so the best part, if you like scale, let me find the poly expand. So if you want to poly expand a bit more, let's say 17, it will perfectly account for it. It will scale it automatically and everything will be absolutely correct. So let's go back. Yeah, as you can see, very flexible. So let's go up. So now after we made the arcs, so let's unpin it. The next step is to make our fences, which is very simple because we kind of already have the pivots for them. So let's create a null, call it in, attach, collapse, called fence. So let's dive into the fence. And here we already have everything needed. However, there's one thing we will have to check for, and that is stairs, because sometimes stairs can end where our fence is, and since we want to delete a random fence because there has to be an entrance, we do not want the stairs to obstruct the entrance to the fence. Therefore, we will have to check for that. So let's bring object merge. We will bring stairs. So let's grab our stairs point. It will be in the body attribute, stairs point, accept. So here it is. And in the stairs point, we don't need the stair point itself. We need to know where it intersects with the ground floor. It is very easy to account for because we know that our stairs is one module width and one module height. So all we need to do is move it one module to the direction of its normal. So let me illustrate you. Put on ground. So all we need to say that first of all, put it on the ground. So it has to be py0. We don't need the normal of y anymore. And the normal is a normalized version of its normal multiplied by 2 because we need the normal vector of number of 2 because that's our grid size. And our position is just simply we will add a normal to it. So that is what happened. So let me show you on the grid. So if we have a grid, 20 by 20, which is apparently too small. Okay, let's have it 100 by, oops, I got it. 20 by 20. Okay, rows 2 by 2. We will divide it. Bigger polygons 2 by 2. So our stairs initially was here. So if I put it in the ground, it's here. So this is where the connection of the stairs will happen. However, if you look in the module file, so file, and I will bring the stairs to show it. So stairs body frame. you can see that it is exactly one module length. That is why if we know this point in height, we definitely know where it will end. So that is how I calculate from this point where the stairs will end. I always know where it will end. It will end on the end of the tile.
So the way we're going to identify which point we cannot delete of the fence points we have is by looking at stair points. So we have the point where the stairs intersect with the ground. So I will call it here stairs ground. And we also would need the stairs origin. So here it is, stairs origin. So the way we're going to identify our point is, let me change the color to, let's say, green. So let's say that our fence point is here. So we're going to look around this point. So that's where we're looking around in certain radius with our PC find. And we find the stairs origin, or any stairs in fact. The next thing we're going to check is we want to see whether it's normal. So it, for example, points in this direction. And we want to see the tip of its normal. What does it have in a certain radius? And if it finds the second stair point, that means that this fence point cannot be deleted, because if we delete it here, our stairs, so let me grab the stairs color, will actually go something like this, and we're looking from the top. And if we place our entrance here, it would be abstracted. So that is the way we're going to identify our fence that cannot be deleted. And this works because, for example, if our stairs on the contrary would be pointing this direction, yes, the first check would still find the stairs, but the second check wouldn't find anything, which means that this point could be deleted. So let's implement it inside of Houdini.
So here we are, back in Houdini. These are our fence points, and we already have our stairs that is on the ground here. Great. So now all we need to do is to take our origin point. However, it is not in the correct Y orientation. So what we have to do is we have to take our stairs point, this one, and just translate it on $$y maximum. So this way we put it on the ground as well. So these 2 points, we're going to merge them because we do not care which one is which when we're going to check for them. And we're going to check for them in a wrangle node. So let's grab a wrangle node, connect our fence points into the first input and the points of the stairs into the second. We will call it delete random and make sure trans over points. So first thing we have to have is a seed. So let's grab a seed. So seed channel seed. Let's create it right away in here. So great. We would also need a maximum number of points. So let's grab that. So int maximum point is endpoints of 0 index input -1. So why do we need to know it? It's because when we're going to create a random number, so random number, we want to have a random number that will go between 0 and max points. So it covers all the range of the points we have in the 0 input. So let's do that. Let's grab a random of our seed. And we're going to fit it between its original values, so 0 and 1, to 0 and maximum point. We would need to print it, and we would need to convert it into an integer. And don't forget to put a semicolon in the end. So what we're going to do now is we're going to compare the current point number to the random number. And if they are the same, we want to delete that point. However, before we delete it, we will make that check that I illustrated you in Photoshop. So we will need to create pcloud1, where we're going to PC open first index input where our stairs points are, p channel, original position of our current point we're running over, smaller radius, and only 1 because we do not need to store more than 1. So for the next pcloud, we would need to know the new position. So let's grab a vector. We call it normal tip, and it's a current position plus normal. So with this information, now we can run our second PC open.
It's absolutely the same, except for in the position we'll put normal tip. Again, small radius and only one. So now, if PCNum_found of pcloud1 plus PCNum_found of pcloud2, so if both of the pclouds returned 1 and we have 2, that means that this point cannot be deleted because it would create an entrance that would be abstracted by the stairs. So what we want to tell it to do is we want to modify the random number. I would say that the random number is random number plus 1, but sometimes it may exceed our maximum point. So what we want to do is we want to tell it to have a modular of endpoints of 0 index input. And in here, before we exit the if statement, we want to remove that point. So remove point, and we will remove the point that has the random number. Just like that. And here we will actually tell it to check for stairs. And we say if point and its normal tip touch the stairs points, modify the random number so that the point is not deleted. And before we apply the sept and close our wrangle, we want to assign a name, because all the points that are going to be left are going to have a name of a fence. So fence. So apply and accept, no errors, that's good. So as you can see, we're always randomly deleting some point, and currently we can delete any point because our stairs do not influence our outcome. So as for the seed, let's go up and grab the seed from here. So copy parameter, paste relative reference and add some other number. And one more step we have to do is to add an additional switch, because sometimes we do not want to have fences at all, because it will add some visual variety to our houses. So as for the switch, we will also use the seed, so paste copied relative reference, and we're just going to make it 50-50. So let's have a random of that seed, and that is our 50-50 chance. And then let's actually have this here. So in this case, we have the fences so we can see them. So that's it for the fences. So let's go up, connect the fences to our merge, so we have it with everything. And yes, up again. So here are our fences, nicely placed. And that is our entrance. Beautiful. And as you can see, the fences are automatically scaled according to the length of the normal. And that's because they inherited the scale from the arcs. So yeah, that's it for the full support. And in the next part, we will deal with partial supports. And I'll see you then. Thank you for watching. Bye-bye.
So now it is time to place our partial supports, for which I changed the seed to 248, because here we have a nice case of a partial support as well as the full one. And in supports, let's bring in null. Let's collapse into a new subnet, which we will call partial support. And if you remember in the very first chapter where we were creating the base, in the closed balcony, we found this find closed balcony where we already identified the normals for the partial supports. However, we did not pass these normals to this one. So that's what we will have to do now. So let's go back to the supports. Go back to the partial support. We will need to bring in our find closed balcony in create body base and in closed balcony. So in here, what we want to do is we want to find the closest primitive to this, because sometimes we can have multiple ones. So let's first locate our support. So type support partial, primitive delete non-selected, and we have this, and let's transform it up. Or actually transform this down. No, this one up. Yep. Let's call it up. Translate 3. Yes. And what we want to do now is we want to create a for each subnet. which we will run every time for the number of primitives in the first input, so n-prims op input -1. And we will call it inherit normals. And what we want to do is we want to find the closest primitive to this one out of the find small balconies. So here we want to say that sort, and we will sort the imported balconies, proximity to a point, centroid of, I mean, here we will have to create a new blast where we will locate our current primitive. Primitive, delete unselected, yes, and we want to centroid of the locate 0 dx, yes, dx and dz. So here, this one will be 0. We always need the 0 one. 0 didn't selected. That's a primitive. So this one is now very easy. We just want to grab a wrangle, attribute wrangle, and we want to inherit the point normals. So it's called inherit normals, and for each point, yes, all correct. We just say that the normal is absolutely the same one as the point of the first index of the first point in that index. Yep, that is what we have. So after that is done, we will create a new subnet just to separate logically, so it will be easier to find later. Just absolutely the same. Procedure, and this one we will call support partial, because that's where the main assigning of all the attributes will happen. And here, let's just copy this locate. So now I want it, yeah, copy. And here we want to convert it into a line. Actually, in this one we do not need locate, so here you can just say each primitive. Each primitive, yes, it will be just easier. And here we just need to convert line, because we only want one of those lines, and show you in a second which one. We want to sort the points according to the normal which we inherited earlier. Sort by normal. So point along vector, and so 0 here, and point. We will just say that we want the one from op input path, the one that is connected to us in the 0 index. It's 0 and 0. And here it's 2. Yeah, all correct. That's how we sort. And the next step is we want only to keep the points 0 and 1. So blast. We want to keep 0 and 1. Delete non-selected, not primitives points. Then we want to identify all the variables, so wrangle. So let's call it initiate attributes. And for every point, we just want to say that the folder is support. Type is support partial. And name is arg, and variation is 1. Variation is 0, 1. Yeah. And the another thing we want to check for is the full support. So let me find you the case that illustrates you what I'm talking about. So for me, it's seed number 6,
And as you can see, it features both full support and the partial supports, which also rests on the full support. So in those cases, we want to make sure that the partial supports perfectly sits on the columns. So it needs to be dependent on the columns. So the way we're going to do it is we're going to object merge the full support. So we just bring the whole thing in. So full support, accept. So that is it. So we want to transform it up by 3. And we want to make a new wrangle. So we say that it will be called check for full supports. So then here, first of all, we need to say that don't run it if there are no points. So if on endpoints of the first index, so if there are any full supports, only then run the following code. So we want to know how many points there are. So we will need a close PT array, and we will use a function called PCFind. It's like a PC open, but it returns us an array from the point 0.5, 1, so 5. So we're trying to find the points, the closest points in the radius. So we say that if length of that array that got returned to us is bigger than 0, something was found. It's just another way of writing what we already wrote before with PC open. We say that PT is a close PT0, so the closest one. We want to know its position, so we will write 0.1 PT. And we need to move only in the axis perpendicular to the normal, because when we have this, and this is our normal right here. Where's our normal? Yeah. We don't want to move it like in this axis. We want to move it in this axis because we want to make sure it snaps perfectly to the column and it sits on the column rather than awkwardly sticking out. So that is why we need to know which where is the perpendicular of the normal that this point has. So that is very easily done. We call it a vector move, and it's a cross, so perpendicular of the normal and the up axis, because our normal can never be up axis. So, and it should be an absolute one. And here I will make a small trick, because once we got the vector, what we want to find out is which axis is not equals to 0. We want to find out which axis of the cross product is 1. So the way I want to do it is I want to create an array. I will append to this array all the vectors components. So move y, array, move z. What I will do is I will find an index. I say find in which our array index is equals to 1. And only in that index I want to move my point. So only in that index. And only in that index I want to inherit from the point of the column. I want to inherit the same position. So for some reason nothing changed, so let me check. Okay, I found a mistake. Just make the radius a bit bigger. 1.5 apply. And yeah, it's just I made a print to find the mistake. So apply, and this way, as you see, it snapped to the position of this point in the axis perpendicular to the one that it has the normal. So I'll show you in a second the difference, the visual difference. So if we merge full and partial supports together and replace the modules, And oh yeah, don't forget to make the scale because right now it just collapsed them. Don't forget to mention that the scale is a 1. So in initialize attributes, don't forget to say that the scale float scale is 1. Yeah, and it's, I guess I mixed up the normals, so it's an easy fix. Let's go for check for full support, blah 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 blah. First of all, reverse this, and we need to reverse the normals. So so when I was inheriting the normals here, and we were inheriting them, we want to say that it's a minus. Yes, that's correct. So and I was showing you the difference. Yeah, I remember that. The reason for that is that it complains about the scale. So if you create a scale and you say that it's a vector and it's always 1 1 and 1 and its default is 1 1 and 1, might solve the issue. Let's see. No, yes, and it did solve the issue, because in copy, if you create a scale parameter, it kind of reads it in here. So let me check what will happen if it's a float. Yeah, just create in the beginning like a safety check of scale, because somewhere along the road it just zeroed out our scale for the partial supports. But what I wanted you to show initially is, yeah, you can see that our support does not rest on the column. If you're not checking for it, it looks kind of awkward and ugly, and it just does not make sense, because this is like a good placement. That's how I would build a house, you know. So that's why when you go in support, make sure to enable the check for full support. It nicely rests on your column. Oh, it just pleases my eye. So yeah, that is all. That is all for the supports. In the next video, we will be placing stairs and all the sets for the stairs as well. And I'll see you then. Thank you for watching. Hello and welcome back. So in this video, we're going to place the stairs. So let's start. So let's bring in, as usual, null. We will need to connect the body attributes, because it contains the door and the stairs, and collapse it, and we will name it stairs. Let's color it right away. Yeah, in the correct shade, and call it in. And in here we will need to grab our stairs point. So let's locate it with blast. And if I'm not mistaken, we made it always number 0 points. And I'm not mistaken, I think, am I? Actually, I am mistaken. So let's go back to body attributes. Okay, so we actually put it in the group. Okay, that's even better. So then we just need to grab the group. So just grab the group, stairs point. Awesome. We will call it stair point, and we will have to move it because our stairs will have a small walkway. Like I'm just gonna show you. Let's grab the file. Let's show you how the stairs body looks like. And as you can see, it is placed in the center. The pivot is in between the two rails. So that means that our pivot has to be a little bit to the side. That is why we will have to move it. And to move it correctly, we need to grab the door. So let's do that. We will just say we need the door. And not just any door, actually. First, let's locate the top floor. Top floor. And we just say that we want to delete all the points with p if its position in y is smaller than 3. So delete non-selected, yes, correct. And from there we will grab our door. So we need to say that the type is door. And delete non-selected, it's a primitive, and here it is. Amazing. So let's grab the wrangle node. And we will move the stair point based on the door. So the stairs is first input, door is second. We will call it move. Let's bring it a bit bigger. And what we want to do is basically we want to grab this normal, and we want to move this point according to the normal of the door. So that is why we need the door. And it is very easily done. Grab the normal, vector normal, from our point, from the first index input. It's a normal, 0, normal, yeah, that's correct. And we just say that the point position is set. Well, technically we don't need to set. I wanted just to make sure that y is 0, but y is going to be 0 anyway. So just say that it's a normal divided by 2. Apply. And yes, that's correct. And y by 2 is because we need to move it only 0.5. And that is based on the module, just calculation from the module. So if you're working with someone else, make sure that all those calculations are discussed so you're aware of those, of all the dimensions. And whenever I work with someone else and they do the modules, if they haven't finished them yet, I just use a placeholder. But yeah, make sure that you discuss the dimensions beforehand. It's otherwise it might be a bit painful to redo everything, to do all the dimensions. But yeah, so now we will make our body out of it. So body consists out of a frame, which I showed you previously, and steps. So I will move it into a subnet right away, just to make sure that everything is structured and in nice folders. So this folder will be called body. I will color it right away, and in here, let's call it in. Make sure that our point, so set normal, and actually just init attributes. I want to make sure that it's normal in y is equals to 0, because we do not need the y information. Also make sure to name it as name, frame, and as variation is 0.1 because there's not going to be any variation. And as you remember, folder is stairs or stair. Let me remind myself. File. What's the name of the folder? Stairs. Okay, it's with S. Stairs. And type is also stairs. Technically, we can just forget about the folder and we will just use type of the folder as well. So init attributes all correct, yes and yes, and we will also need to wait. Where is our point? Yeah, that's it is. And we also need to make sure that our steps are placed correctly. For that, we will need another attribute wrangle. So wrangle. So in here, I want to make sure that from this point, we will generate the steps. So let's say steps. So let's bring it bigger. So currently our normal is under 45 degrees. So we want to make sure that it is not. And it is easily done. We know that our module is 2 by 3, 2 in width and 3 in height. So we just need to say that it's 2. And this is 3. Oops, and y, and this is 2 multiplied by in x. So should be working. Oh, and z, sorry. Apply accept, and yeah, as you can see, our normal is now changed. It's now at the correct angle. We will also need to start our steps a bit lower, so make sure that we will move our initial point a bit. So normalize, and we want to move it only in x and z. So we will need to make a new set, and it's we only need to grab the x and z and 0 in y. Z, and just a smaller number like 15. Apply. So yeah, it moved a bit to there. That's all correct. We need to make sure that we know where it intersects with the ground. And that is very easily done. First of all, let's say that we find the point of intersection with the ground. Since we know the grid modules, it should be easy. We just need to say that vector ground pos. And as you remember, we just need to say that we want to subtract. We want to say minus set.
and we want to normalized version of our normal, and we want only the multiplied by 2. Hope we can do it like that. Let's see. -3 is also minus, and this is the same. We just need to grab it here, and we just say it's easy. So let me test this actually till we do anything further. Okay, I found a mistake. So because n.x is not actually equals to 1, because once we normalize this, this will be, because the length of the total length of the vector is 1, not in its axis. So this is not equals to 1. So we just need to say that if nx is not equals to 0, and here and z not equals to 0. It should work. Let me check apply. Yes, so now that looks more like truth. Just make sure that it's a very important thing because let me check, show you. If you go to spreadsheet and you find your see, those numbers are not 1. So the only thing we want to check is whether it is equals to 0 or not. We don't actually need the number 1, all right, like or the value of the vector itself. So we figured it out. Now we need to create a line. So let's say start the line, and it will be a primitive. So we say add primitive, and it will be a polyline. And we want to just resample the line. Sample the line, and we would float steps number, and it will be a controllable thing. So we say steps number channel. Apply. So the direction vector is quite simple. It's just the ground position minus our initial position. And we also need to add a pt. It will be a variable to hold our points, and we will create it with a function add point, and also the position, the new position, because every point will have a new one. So also set variation. So here I will explain how to set variations. Remember, we were always writing 0, 1. Well, in this case, there are actually 3 types of variation. I included just to demonstrate that you can do it with any module. Like if you have you can have like 10 windows, 5 different stairs types, or even in sets, like maybe you can create a new attribute called set, and then you will like write it into the name. So it's not just like in my version, it's not just stairs body step 0, 1. Maybe it's stairs, but and then you should write like a set stairs medieval, then body step 0, 1, and then you have like stairs Victorian body step 0, 1. So you can really expand this system a lot. So, and this is just a small things I will show you, and you can really easily just expand on them. So one of them is just adding more variations. So we will just say maximum variation number. It's 3, but is it 3 actually? It's been a while. Yeah, it's 3. Okay, it's 3. So I also will need the seed. So channel, seed, and random number. So then we will need to get normal from the body. So get normal from the body, from the stairs body. Get normal from the stairs body. For that we will need to connect our stairs body into the steps. Okay. Yes, and just grab the vector normal, and it's a normalized version of point, and just first index, normal, and first point. Apply. So now we will need to create all the points for the steps. So we will need a loop int, and we say that it will start with x equals to 1. X is smaller than number of steps, and with every step x is bigger by 1. So technically you can do it for every module. Like you can have 100 steps variations. You can also make them procedural, bake them out, and bring them into the system. So let's identify the position. So the position is always our initial position of the point that we are driving from, plus direction multiplied by, because our direction is like the total length of where our steps will go. So every time we need to just take a part of it. So it's x divided by steps number. And random number, is going to be driving our variation. So yeah, it's just the usual routine, random of seed plus x, and we will fit it between 0 and 1 and 0 and our maximum variation number. And don't forget to round it to the next integer, and also don't forget to convert it to an integer. The rest will give us a warning. And yeah, so now we can can create a new point. So add point 0, and we will already know the position. And yeah, and we add that point as a vertex to our primitive. So 0 primitive, the one we create as a polyline, if you remember. And yeah, add that point. And now we need to add all the important stuff to this point, which are the attributes, because that's what's the most important, right? The attributes that will drive our placement. So we need to add variation. So variation, a point, and we will print f. This will convert this will convert anything into a string. Since our number is just a one number, and we have like 0, 1, 0, 2, then you should just wait for 0 and d, and then we write comma, and whatever we write here will be placed where the d is. So then we just write set. Oops, set. And then we also need to set lots of other stuff, so just copy this, save us some writing type. And yeah, we also need to set name, and the name is step. Just copy all of that. And also normal, and it's normal from our body. And scale, and scale is I actually had to make it a bit smaller, so 0.8 in x and 1 and 1. And we don't need the original point, so remove point 0, 0. Apply. And, well, where are all the points? It's just the steps number. We have 0 steps number, so let's make it 10. And voila! We have this, we have this. Beautiful. The only thing right now, like we all made this, all the set point attributes. However, if you go inside, you're not going to have any of them. So why is that? It's because these attributes do not exist yet, so we will have to create them. So before we go into the in, we will make a create attribute. And I'll just say init attributes. And it's going to be a bit of them. So the first thing is name. Oh, we also forget the type. Did we say the type here? No, we did not. Okay, so name, it's a point string. We also want to create the variation. It's also a point string. We also want to create type, which is also a point string. What else? Name, scale, and we also want to create a scale, which is in this case it's going to be a vector. So and don't forget to put the values 1 here. Otherwise, if it's default 0 when you will have your copy place, you will not see anything, and you will be like looking for an error, but it's simply just shrinked your module to infinitely small. And let's also go a bit back here, and we need to set type. Type. So here's type. And you want to make sure that its type is stairs. Apply accept. So here we're all set. Yes, awesome. So yeah, that's our steps. Now we just need to merge them. Oops, I think I brought something else. Yeah, merge together, and that is our pivots. So let's go up. And now we want to place modules. So what I'm going to do is I'm just going to copy place modules from the support subnet. And yeah, it will complain because it doesn't have we don't need the scale here. And in our file, it will complain because we don't have the folder attribute anymore, but we just say just take type, apply, accept. So it should work.
Let me check. So do we have a point in here? Yes, and okay, what's wrong? Stairs, frame. Because we forgot to mention that this is a body. Because if I'm not mistaken, let me grab the file. Yeah, it's a body. So we also need to make sure that the type is a body. So yeah, we will have to still separate folder and type. So, or we can just add it to the name actually. So the name is yeah, I think that's gonna be better. Less attributes is always better. So let's just add body frame, and here as well is a body step. So now should place something. Okay, it says there is no stairs body step 0, 0. Yes, that's one of the problems because as you remember, we in our random number, we set it to go from 0 to maximum variation. That's incorrect. It should go from 1 because that's our counting in our file starts with 1. So make sure to correct that. So accept. Okay, now it's placing something. That's always good. And let's see. So it placed our body, but not our steps. Placed only one step, which is surprising. Okay, let's look at this again. It doesn't. Oh yeah, because I forgot to put copy. So now it should be correct. Yeah, so merged together. So as you can see, all the steps are a bit different. It takes different ones. To illustrate it even better, I'm actually gonna show you one thing. Just gonna create a font note, and we're gonna say that please write point S from the locate, and we want to know the variation number. And don't forget the brackets here. Oops. Yes. Yeah, awesome. We want to merge it with our steps. Yeah, and we just want to show that it's, and just make it a smaller. Yes, 0, 1, amazing. Copy it, and you will see in a second why I did it. Is because we can see now all the steps and which variation number they are, and the body also has this 0, 1 because body has only 1. So yeah, you can like make check for that if you would like in your global settings, just to switch on and off the variation number or even the set name. You can like check in anything, any attribute you created, which is really handy. So we don't need this for now, so let me delete those. So that is the stairs body. So now we will move on to the stairs walkway. So the next step is to make the walkway. So again, let's start with a null and collapse it in a subnet that we're going to call walkway points. Actually, just walkway. Let's be consistent. And we will color it in the same color. And let's dive into it. Call it in. So the thing we need to bring in is not the move points. The thing we're going to bring is the top floor, because we're going to derive from the door. Not just any door. I'll just show you what I mean. So first of all, let's remove the unused points by getting an add node and delete geometry. Remove unused points in polygons. So we'll call it remove unused points. Okay, great. So what we're going to do is we're going to bring also the door. So let's do that. Door into the second input. And here, let me bring another null. We'll call it indoor. And this one is going to drive the primitives that we're going to select here. Because we don't want just one walkway primitive. We want it to continue for, I don't know, 2, 3, 1. It should be random. We don't want it always to be just one. So to do that, we will bring a delete node. We'll delete by bounding box enable. So we always know it's going to be 3 in size. However, we need to make sure that the sizes of x and d
are correct. And the centroid is also easy. Centroid is a center of our indoor. Indoor. Dx, dz, and dy. So here. And as for the size, let's bring it a bit bigger. As for the size, we want to know the width of the door and the correct axis. So we will need to have a bbox indoor, and we will need to subtract the maximum from the minimum. So that is 1. And we always want to make sure at least a bit bigger, because sometimes it can be 0 and we don't want the size to be 0. We want it to always be a bit thicker. And we also want to multiply it with a random value, so which we don't have yet. So syntax error. Oh yeah, there's a minus here. Apply. Yeah, you happy? Yes, it's happy. Because we want to have a seed. So let's create a seed. So now we'll call it seed. We will color it. We will edit parameter interface, float stairs, seed, and seed. Because I remember we also had a seed in our body here. Yeah, here. So it's in the steps. And here we will copy this into our size parameter. Let's connect our seed to the global seed. So copy parameter, bring it into the stairs, paste relative reference. So now go back into the walkway, and in delete we can now reference to the seed. So let's copy that parameter, and let's bring it here, and I'll just copy that. And we also want to make sure that the seed is actually a random of the channel. So random, okay. So now in here, we want to multiply this, all our width, with a random of the channel. And we also fit 0, 1 to a random number. So let's say it can go from 1 to 4. So it always will multiply to a random number from 1 to 4. So apply. Yeah, just copy that. So yeah, currently it's just one module width, but let's copy it here as well. It's with Z, and Z, apply. It should always be 0, 1 because because the bbox of Z max and Z min is 0, so this is also multiplied with 0. So let me demonstrate you that it can be different width by changing our seed number here. Let's set that down. Yeah, see, it now selected much bigger area, so that is exactly what we want. So let's keep this case. Let's keep as if it's our walkway is 2 modules wide. So, but we do not want to delete those. We want to keep them. So delete non-selected. So those primitives will be the driver for our walkways. However, we do not want just the primitives. We want their bottom middle points. So we'll create a subnet. Get bottom, and we'll say for each primitive. We'll also get bottom mid points. And inside here, let's unpin this. We want to bring in transform node. Oops, caps is on. So in transform node, we will get bottom middle. So what we're going to do is we're just going to collapse to bottom middle point. So by simply utilizing the pivot. So the pivot should be the center in X and Z. However, it should be Y minimum. So Y minimum. So now if we just scale it down all the way to 0, ta-da, that is our point. However, it's 4 points overlapping, so we just need to grab only 1 point, and we will do it with blast. Just say we want to keep only the point number 0. So points, delete and selected. Voila. And the best part is they have the correct normals from the original primitives. So after this is done, we want to check whether those walkways are intersecting with anything like another wall or maybe a roof. So we need to check that. So for that, we will need to grab the base, which is technically like everything, because here, for example, you see that they overlap with each other. So we will need to grab the roof base as well. We're going to connect it to the second input of our stairs. In here, we're going to merge them together. We will say that it's in base, and we will merge the in
and we will merge the roofs. Just put it here. Yep, and we're going to connect it to the third input of our walkway, and we will call it in base. So yeah, so we'll need to grab a new wrangle node. We're going to connect our points to the first input and our base to the second one. We're going to say that it's a check intersect, and it's going to run all the points. So in here, we just want to simply check whether it intersects with something if we ray at a 45-degree angle. So the direction is set its original x, -1 in y, and its original z. So we will also need to grab PV and UVV because we're going to use an intersect function. So intersect, and we're going to intersect it with the first input from our original position. However, we want to kind of offset it a bit. Otherwise, it's going to intersect with our wall. So just a bit. And then we want to check our direction. We're just going to ray it to infinite, basically. And we're going to introduce the PV and UVV. And we say if intersect is like bigger than -1, so it is true, then remove point. So apply, accept, and we should get rid of this. Yes. All correct. This one is gone now because, as you can see, if we ray it under 45-degree angle, eventually it will collapse with a wall here, and that's not what we want. So check intersection, all correct. We also want to make sure that the stairs point is kind of in, like for example, if that is our walkway primitive, and here is another one, stairs kind of goes here. So we don't want any walkways above our stairs, if you know what I mean. So we need to check for the stairs as well. So here we go up. And our stairs point to the last input of walkway, and we will call it in stairs point. And here we're going to grab another wrangle. I'm going to connect the stairs to the second input and our points to the first. We're going to call it stairs check. And let's bring it bigger. So we want to find the direction between the stairs point and the walkway point, and compare the direction to the vector of our stairs. So compare direction vector between stairs and walkway with stairs normal. So let's grab the direction. It's a normalized point, so the stairs point and our current point. So we grab the direction. Then we want to grab the normal of our stairs. So normalize the normal, 0.10. And we want this normal to be only in x and z axis. We don't want the y axis. So set normal x, 0, normal z. And also normalize. And then we're going to compare them. So if rint of the direction is not equals to the rint of normal, then they have opposite directions, which means that this walkway is going to be above the stairs. So then we don't need it, remove point. Okay, so in this case, nothing was removed, which is logical, but I just want to illustrate you why this is important. So if I would to destroy the y, so let me show you attribute wrangle. So it's set n.x0 and n.z, and I'll also normalize. Yep. So the direction vector between them will also point to that direction because we subtract from this one. So the direction of this normal will be correspondent. However, if they're pointing in opposite directions, so for example, a point is here, that means this point is on the other side of this vector, which means this point will be over the stairs. Like this, it will be above the stairs, which we don't want. So we want always them to correspond. This vector direction should be the same. So that is why we're checking for the stairs. So this is just the foundation. So once we have that foundation, now we're gonna start doing all the walkway stuff. First of all, we will need the body. Body is very simple. It's literally just naming this point body. So let's call this body, and we're gonna color it. And it's literally just saying as name is body. So yeah, body is done. Very easy. So the next one, we're gonna do the rails. So we have two types of rails. Because our body walkway, let me show you walkway body. Our walkway body that has like two sides. It has a short one and a long one. So we have long rails that go here, and we have short ones that go here. So this, and it will be two different systems, because the short ones shouldn't go on both sides. Sometimes it shouldn't go on any sides if this walkway is adjacent to others, or only one side if this walkway is adjacent to the stairs. So all of that has to be taken into the account. So we will start with long rails because it's just easier. So we will just need the stairs checkpoint. Where are you? Yeah, here you are. Let me create a null, because we're going to create a subnet. We're going to collapse it. We're going to call it rail long. We're going to die it, and we're going to jump into it. And it's very simple. All we have to do is literally just transform it up a bit. Otherwise, the rail sinks in the walkway body a bit. So this is a number that I found works best. Just say transform up. Then we also want to peak it, because we already have the normal. We just want to move it in the direction of that normal, and don't recompute. And we need to move it in 95. And that's it. And we just need to name it. So attribute Fringle. Rail long. So yeah. As name rail long. So that is two are done. Let's merge them together. Yeah, nice. So now let's do the supports, but for that we will need to create another foundation, which is very simple. All we have to do is let's create another null, call it in, and we will call it bottom line. And let's put this a bit lower. And in this one, all we have to do is literally copy a line. So the line has to be in the direction of z, if I'm not mistaken. Yeah, and it has to be origin 0.5. Length, copy parameter, paste relative reference of the length minus length divided by 2. So it should be on the on the middle, and it has to be the length of 2 because it's our module size. And the last but not the least, we need to attribute transfer. Here you are. We need to attribute transfer the normals from the in. Just the normal. Yes, that is our bottom line foundation, which will be foundation for our rails. I mean, yeah, it's also for rails, but it's also for the supports. Yeah, support beams. So let's bring another null. It's going to be another subnet. We're going to name it support, not in caps, support. And let's color it right away. And let's dive into it. So here we will have to get another attribute wrangle. And in this one we will call it contract line, because we just need to shrink it a bit, because otherwise our column's going to stick out of the walkway body and it's not going to look very pretty. So it's just very simple, couple of lines, and we just say that we need to find its neighbor. So neighbors, 0 pt num, and we just need the first one. And the direction vector is literally a normalized version of 0.0p neighbor and the current one. And we just say that the position is the same one, but we just add the direction and we want to pick it on this value. Apply, accept. So as you can see, we just shrinked it a bit because our direction is pointing to the neighbor. So both of its directions are pointing onto each other and they're moving in the direction on this number. So if I say it's a bigger, it will be bigger. Keep doing that. So yeah, now we just want to fuse it, because sometimes we might have multiple primitives, like for example, if I do not check for intersection, then I have multiple, see? And we want to fuse on a very big distance because we want to snap them. So yeah, that's what you want to get if you have multiple ones. So for now, let's keep this like that, and then we will disable just to account for the errors if we have any. So then we will need another peak for the supports because they shouldn't be stuck to the wall. They should actually support. So that is the value that I found works best, and we don't want to recompute the normals, as well as we don't want to update point normals in the fuse. Thank you very much. And now we just want to add random rotation and initialize attributes. So let's bring every angle node. So remember how last time I was just randomly assigning values to the normals, like normal x and z, and one of them should be 1 and another one shouldn't be 1 or -1. I want to show you another way of rotating, and we're going to do it like this. We're going to say float angle. It's going to be a random number. Random of the, we're just going to derive from the position because this should not really be controlled, I don't think so. And we're going to fit this number from 0 to 1 to 0 to 4 because we can rotate 4 times 90 degrees to go around full circle. We're going to multiply it by 90, but before that we should rent the number. It should be an integer, and then you're going to multiply it by 90, and then we want radians because we're going to rotate it with matrix. Now I want to say that vector 4 is a rotation. We're going to use a quaternion. I say it's a quaternion, yeah, thank you very much, of an angle. So we're going to rotate for the angle around this axis. We're going to rotate around y-axis. And then we say that vector normal is q-rotate, so we're going to rotate this normal with our rotation quaternion, and we're going to rotate it. We're going to rotate our normal, so that's a new normal. And now we say that normal is a new normal. And don't forget to name it, which is just support. Apply and accept. So as you can see, all of them have a random rotation. Let me show you if I delete the primitive, it will be more visible for you. No, not this one, this one. Yeah, as you can see. Voila. And if I just add a different random seed, here, 19. Apply. Yeah, you have different ones. So there's just two ways of doing the same thing. So another thing, yes, that we need to check for is going to be the windows, because sometimes our supports can obstruct the window and it just, yeah, as again, it doesn't make sense. So we're going to bring in the body base, so object merge. Going to bring in the body base. So where are you? Body attributes, thank you. We're going to say that body base, so we only want the top floor, so blast top floor, so py, if it's smaller than 3, we literally do not need it. We also want only the doors and windows. Oh, wait a second, on the contrary, we want only the bottom floors. So yeah, so bottom floor, and we want to just doors and windows. So oops, yeah, I just want to say that we need a primitive, delete and select it only if its type is window or if its type is door. And the next step we're gonna check, let me show you what we're gonna check. We're gonna check whether this point or any point of those touch the top centroid of the primitive, because sometimes if you have like support here, like a walkway here, and since it doesn't cover the full module size, it's half of the size, the support will go here, right in the middle. But if there is a window here, it's just going to obstruct the window. So that's what we're going to account for. We're going to actually check, is it touching the primitive in that particular point? So let's bring a angle, and we're going to say get top centroid. And we want to run it over the primitives. We're going to just say, yeah, let's grab all the points from the primitive. So prim points, 0, prim num. And we're going to say that we want only the 2 points. We need only 2 points. We only need the top ones. So we want to grab PTS 0. And we want, let me just copy it. And we want to grab PTS 3. So vector new position is addition of those two and divided by 2. So add point, our new point,
0 new position. Oops. And we want to remove the primitive because we only need the point. So prim num, and we want to delete the points. Yes, thank you. Accept. That's what we have. Amazing. Exactly what we need. So another wrangle now. And in this one we will delete, let's just call it delete touching, because literally we just touch, if it touches we delete them. And this one we will attrib init. Yep. So in this one, connect our points into the first input and connect our doors and windows into the second one. And let's bring it in, and we will just say that delete the supports that obstruct windows or doors. So, and we're gonna use a pcloud again, pc open. From the first index we will look for positions. From the current position, 0.5 should be enough, 1, and we say that if at least 1 was found from our pcloud, then we don't want the point, we just don't need it. So remove point, 0, ptnum. And apply, accept, and yeah, nothing changed, which is correct. So let me enable the stairs check intersect. Yeah, that is our support. So now let's continue to the rail short. Let's create another null and collapse it into a subnet, which we will call rail short. We will color it as well, and we will connect bottom line. As well, we will need the stair point. So stair point, because the stair point will determine which rail short we actually need. So we have this in, and we're just gonna sort it relative to our stair point. So let's grab another null. We'll call it in stair point. We're gonna sort proximity to a point, and we're gonna say that it's actually just take the centroid shorter to right. There's pt and dx, dz, and dy. So that is correct, and we always want to keep the last point, so we want to say reverse, and we always need only the last point, so we always need the 0 point. So point, selected, here it is. Then we will need to initialize its attributes, so let's grab a wrangle node. Let's call it trip init, and here we will need the stair point as well, because we will need to write a direction. So vector direction is a subtraction of the stair point position and the current position point, and we want to normalize that. Normalize. So now, pay close attention. The normal we will need to divide it by 2.1, and that's where we have to move the position. So let me show you what it will do. So it will move us forward. So why is that? Is because our centroid for the rail is also in the center, so we need kind of to put it in the center of the walkway body. Then we will change the normal to the direction. Yeah, and we will also need to move the position a bit to the direction, so 0.05, I think that should be enough. And we just say that that is our rail short. And note how we always do it relative to normals and directions that we already have. We never bind them to a static, so to say, value. It is always a value relative to that point, and it's very important. So after we have that, we have our rail short. Let's merge it here too, and our supports. And the last step is a rail bar. I will show you what it is, because I'm not sure how to call it actually. It's a rail bar. Yeah, here it is. It's kind of like an ending to a rail, and it should go where the stairs are. So we will need to create another now, and we will call it rail bar. We will connect our bottom line and color it. Let's merge it right away, and in here let's dive into it.
we will need to repeat what we did with support. We'll have to contract the line and fuse it and pick it and so on. So let's copy this 3. Bring it in here. Oh, didn't copy for some reason. Let me try again. Okay, now it will copy. And let's bring it in. So contract the line. We want to be slightly less. Oops. Fuse it absolutely the same way. We want to pick it. And number I found works best is 96. We will also need to bring the stairs point. So let me grab that. Stairs to the second input. Another null. We will call it in stairs. We will sort it again to the proximity to that point. So proximity to point, centroid of the in stairs, dx, dy, and the last axis dt. And after that we will just always delete first one. So because our why we're deleting the first one is because our body, stairs body frame, already has those rail bars in them. So we do not want the first one, sorry. So we always want to delete the first rail bar. Yeah. And now we want to initialize the attributes. So we will actually copy it from the supports as well, because I want to use the same principle of the rotation. Oh, it's delete touching, sorry. This one, yeah. Bring it in our rail bar. And in here, just make another random value. And we want to name it railbar. Railbar accept. So here is everything that we need. All of our points. However, they are missing the folder and type. They only have the names. So that's what we're going to do now. We're going to assign them. So attribute wrangle. And we will say that the folder is stairs. Yeah, folder is stairs, and as type is stairs walkway. I think that's how we decided to do it, if I'm not mistaken. Let me check the body. We wanted to type stairs, and oh, we just added it to the name. Okay, then let's do the same here. And we just say that the type is stairs. And the name is as name is equals to walkway plus the name. So now, if you check the name, it is always walkway. Oops, yeah. So attrib init, I'll just call it attrib init type. So yeah, and now we should be able to merge them with our place module. So actually, let's test it like here. And we have an error because it doesn't have a... Oh yeah, we forgot to name the variation. The variation is always the same in this one as well. So variation is always 01. So now, as you can see, everything is nicely placed. Oh, just makes me very happy to see nicely placed modules. So let's merge all together with the stair body. And here you go. That is our stairs. Nicely placed. So let's merge it with our support and everything else. That's it for this one. In the next video, we will continue placing the missing modules. And I'll see you then. Hello and welcome back. In this video, we're gonna place our set dressing modules. So let's dive into it. Let's again bring in the null, which we will collapse into the new subnet, and we will call it set dressing. Let's color it to the blue, darker blue, and let's connect the body base to the first input. So let's name it in. We have multiple types of set dressing parts. I created a paddle for you, so I'll show you all of them. So there is a paddle, set dressing, paddle, which we'll place near the bottom walls. There's also going to be crane to place on the walls. And there's going to be
box and barrel. I named them both boxes because technically for me it's for the system it's the same kind of type of module, it's just different variation. That is why both of them are called boxes. So we will start with the paddle. So let's create another subnet. We can just take this null actually and just collapse it into the subnet, and we will call it paddle, and let's color it and dive into it. So the first thing we want to do is to isolate the primitives that we want, and we can make lots of blast nodes. However, I just find it easy just to bring one Wrangle node and have all the conditions in one node. So let's call it del unneeded. And then here our conditions are, first of all, we don't want any point that is bigger than 3, it's position-wise bigger than 3, or if it's a floor or a ceiling, and we don't want anything that is cannot be used, because if you remember previously we were creating this attributes of a wall, and one of them we shaded it gray just to show us visually that on those walls nothing can be built. So that is why this will be our driver in here as well. Apply accept, and which reminds me that let's go up. The first input should be body attribute because that's where we colored our primitives. So that is what we have. We also have lots of unnecessary points, so let's delete those. So let's bring in fuse, and we say remove generate, and then we need to bring the unique points back. So facet and unique points, yes, and post compute normals. So yeah, that is what we want. So let's call it unique points, and here delete extra points. So now we are ready to scatter, so to say, place our paddles. And what we're going to do is we're going to, for every primitive, we will find a zone where the paddle can be placed. So for that we will need a subnet, so for each subnet. And we will call it paddle location. And we just say that it is for each number 0, and we will run it as many times as the primitive in our first input. So op input path index 0 and -1. Okay, inside we're gonna locate the primitive, so blast, name it locate, and again we will write the stump function. And group type as primitives and delete non-selected. So first of all, we don't want the paddle to be spawned right on the edges. That is why we're going to use poly expand node. And we're going to say it's only inside. And then we will bring in a clip node because the area we want is only on the sides here. And the reason for that is that we want to avoid windows. And we do not know which primitives are windows, if I'm not mistaken. Let me check. Yeah, it's type wall. Okay, so we do know which ones are walls and which ones are not walls. Then we will have to create a switch. So for now, let's imagine that this is a window. And if it is a window, we need to bring a clip node. So the origin of the clip node is going to be the centroid of our locate. So centroid locate and dx, dy, and dz. We will keep all the primitives. Distance is going to be 0.5, and the direction is going to be determined by the normal. So direction is point, but it's going to be an inverse one. So here we're going to grab the z. Here we're going to grab the, oops, copy that, and here we're going to grab the x and 0. So here it is, and then we will copy this clip, and the only thing we need to change is to set the direction to minus. So then we're going to bring a measure node. We're going to measure the area. We're going to sort by area because we want to delete this middle part, and the best thing is to do it is to just delete it by its area. So we want to sort primitives by an attribute, yes, and its name is area. So right now
it will be 2, so let's reverse it, so it always 0, so the biggest area value primitive is going to always be 0, and then we can just delete it. So primitives 0, delete not selected. Yes. So the next step is to isolate only the bottom edges of the primitive, and to do that we're going to sort by y. Sort by y. Let me see. Points sort by y. Yeah, all correct. And we're gonna blast. Actually, we do not need to sort. We just need to say that if py is smaller than 3, we want to delete non-selected 2. Oh. No spaces. Yes, and delete non-selected. So everything that is smaller than, we can just say 3. Oh, they're actually smaller than 3. Okay. Oh yeah, we probably expanded, that's why. So everything is smaller than 2. We will keep only this point. So keep bottom, delete middle. And here we want to sort again. We're gonna sort by the sort them by the cross product of their vector, and to do that we're gonna say that we want to do it along vector, and we just say that it is a cross of 0, 1, 0 and point normal. So, and the normal of the input node 0 and n. Yeah, cross. Yes, apply. And gives me an error because... Okay, fair enough, we will do it a bit differently. We'll just subtract the... Let's actually copy this. We will subtract the position of the point number 0 and point number 1. So apply. Actually, this is not correct. It's 0 here and 1 here. Copy that, apply. Yes, happy, good. And this one is the same, but for the z-axis. So here is 2 and 2. Apply. Yes, perfect. So once it is sorted, we will bring a wrangle node. And we will connect those into 2 polygons. Since we know that it's always going to be 4, we're going to say that int primitive 1 is at primitive 0 polyline. And we just want to add vertex. 0, it's primitive 1, 0, and 1. And just copy this, and primitive number 2, 2, 2. And here is going to be points number 2 and 3. That's the points we're going to connect. And here, let's comment it and let's say connect the points into 2 lines. Apply, accept. And right now it's running for every point, which we don't need, detail only once. So here are 2 polygons. And let's make a switch. So all this until here and here. Is for the case if it's a window. But if it's not a window, then it can be spawned anywhere here. So it becomes very easy. We just need to grab 0 and like 3. So let's sort, let's keep bottom. We will need to copy this. And we just copy this. And we just delete this part. And we will create a switch. And we need to only do it if the type is wall. So point S of locate 0 type 0 is equals to wall. Let me check. Switch apparently doesn't really like strings, so we will work a bit around it. Let's just create a small wrangle. We will just call it a switch check. Not going to have any function at all except for if prim 0 type 0 is equals to wall, switch equals to 1. That's all it's gonna do. And here we're gonna say point, oops, point
of the switch check 0 switch 0. So yeah, so that is gives us 0 right now because it is a window. Yeah, all correct. Since this is a window, we have only this once. Perfect. And the last thing we want to do is also to put them on the ground, because right now they're not on the ground. So don't forget to add py equals 0 in both of the connect points. Oh yeah, they don't run over the points. My bad. Let's create another wrangle that we'll just simply put on the ground. Call it put on the ground. .py equals 0. Yes. So, and as you can see, we get a nice blueprint of our building. And the next thing we want to do is, since we have the area, we can now just simply scatter points. So scatter. We don't want too many, definitely not 1,000. Let's make it like 5. And before we do that, let's create a seed so we can make it procedural. So no, no, please. Apparently, Houdini refuses to create a null node for a very interesting reason. Okay, if I copy one, okay, it does copy, so okay, I just copy it for now. So let's create seed, let's color it. I think it was this one, yeah. And we will create a float, which we will call set dress seed, and here just seed, apply accept. We will copy this parameter and we will bring it into the scatter. Paste relative reference, and not just bring it, but we will take a random from this channel and we will fit it. Let's say minimum is 3 and maximum is 7 petals you can have. You can have any other numbers if you'd like. So currently we're having 6. And oh yeah, let's actually round it. Round. Yes. Good, apply accept. So now we have these points, and what we want to check now is to check for full support, because sometimes it can be in the way of the columns. So we will need to bring in object merge. I hope Houdini creates a node this time. No, it does not. So let me save and I will restart Houdini. So sorry about that. So let's bring an object merge, and we want to grab the full support. So full support. It's in our support, and it's full support accept. So here is the points of our full support, and we want to delete anything that is too close to them. So another wrangle, we will use point cloud. Let's call it delete too close. And here we're going to have 2 conditions. First of all, we're going to delete too close to each other. So if they're too close to each other, we don't want the petals to intersect. So we're going to say that no, thank you. So we say PC open 0 P of the current position. Let's say 0.3 should be enough. And then we want to delete too close to the full support. So we say another P cloud. And we say the same thing, but with the index number 1. And maybe a smaller radius. Oh, well, actually the same is fine. 3. And then we say if PC num found of P cloud plus PC num found of P cloud 2 is bigger than 1. And why 1 is because in our P cloud 1, there is always going to be 1 because it's always going to find itself. So we need to account for that. So if there are more than 1, you want to remove the point from the 0 index, PT num. Apply accept. Yeah, we actually did delete some point. Yeah, here. So if we created a petal there, it might have intersected with a column. So we just avoided case all along. So we deleted too close. And the final step is to create the attributes. So attributes initialize. So the name is going to be petal. Variation is going to be only 1. And if you're making your own modules, you can maybe create something else that is also on the wall. I don't know, like a fishing net or something, because technically it will use the same kind of logics and so on. It can be placed in the same group. So the folder is set dressing. as well as the type. I think the type is also addressing. Let me just double check that file. I think we can actually just get away with one attribute here. So modules, addressing, yeah. So let's just keep the folder in this one. So apply. And we also want to make sure that the scale is correct. So scale is always 1, 1, 1, 1. We don't want to scale the pedals. So here we are, that is our pedal. So now we want to place the module, so I'll just copy it from the stairs. Don't load anything, please. Just let me copy the place modules, and we will place it here. And it's complaining because it cannot find the... Oh, we used the type here. Sorry, my bad. Let's rename the folder to the type. So folder, it's a type. So here we are, that is our pedals, nicely placed. So the next step is to place the cranes. The approach is quite similar. Again, let's bring null, collapse it, call it crane, color it. We also need to start with the body base. And we will need the same principle of bringing wrangle and removing unneeded points. So let's call it remove unneeded. And oops, yeah, points as the same idea is to delete the ones that were colored to be gray. Or if it's the bottom points. Because for the cranes, we on the contrary need only the top floor. So remove point from 0 index, current point we're running over. Apply. Yeah, double equal, apply, accept. Okay, nice. And again, we have extra points. We're just gonna get rid of them by fusing. And actually, that's it. We don't actually need the unique points in this case. What we want to do now is kind of see which primitives can be considered outside ones, the ones that actually touch the main outline of the building. So how are we going to do that? Well, we will have to bring in the body base. So let's go up and to the set dressing, and we will need the body base. So let's connect it to the crane, and in this body base, actually, we don't actually need that. We can just use the footprint. We can just use the footprint we created earlier. So let's make an object merge, and we will go to create body and building footprint. Let's say building footprint. We'll have to transform it up. Transform up. It's already divided, if I'm not mistaken. Yes, amazing. So fuse. Actually, we need to divide. We need to remove the shared edges because we only need the outline. So this one, uncheck convex polygons and check remove shared edges. For some reason, this one is here still. What if I fuse? Still, it's an interesting one. Still treats them as two separate ones. What might be the cause for that? Check the normals. Yeah, the normals are the problem. So we're gonna deal with it like we dealt with the roofs. So let's bring wrangle. Very, very primitive. And so we will take all the points, prim points. 0 from the prim num. So it should be an array. And we say that if point 0 and PTS 0 is not equals to 0, 1, 0. And let's just round it just in case. So if the normal of the primitive is not pointing upwards, we need to rewind it. So before we do that, let's make sure the
normals are correctly computed, so post compute normals. Yeah, some of them even pointing to the side, which is a bit odd. Yeah, unique points fixes that. Okay, so face it, unique points, and post compute normals. So, and in here, we say that if it's not true, for loop where integer x is equals to 4, x is bigger or equals to 0, and x minus minus, we'll create a new primitive. So int primitive and add prim 0 poly. So, and it will have a opposite vertex order. So we say add vertex to the primitive, and we add PTS of x, and we remove. After this is done, we remove the primitive prim num. So rewind the primitive vertex order. Apply, accept. So let's see now. We have an error. Forgot semicolon. No matching function for remove primitive. Oh yeah, remove the points as well. 1. Apply, accept. Okay, I found a mistake. So here it should be 3 because the maximum index number is 3. So sorry about that. Just make sure that x is equals to 3 here. And after you did that, you just need to put the facet again, and here you are. All your once you post compute normals, everything is just works nicely. So rewind prim vertex order. Oh yeah, it's my it's my checks. So it's my printf here from checking. Yeah, everything works correctly. And here, if we remove the shared edges, should work also nicely. So let's add views. Yes, perfect. So once we have that, we need to mark the outside primitives. So let's bring another Wrangle node. We will connect our walls of the top floor and the footprint of the building. We will call it outside prims. Let's bring it bigger. So it should run over the primitives. And let's start with, again, bringing the points array. Prim points of the one we are checking. So what we are going to do now is, again, we're just going to look for the points of the outside blueprint of the building, like the footprint of the building. We're just going to look for those points. And if there are some, then it is an outside primitive. But if it doesn't have any, then it's an inside. So we also will need a found. For each, we're going to check each point. So P and PTS. Position, again, the same routine. PT. P cloud is PC open. P position 0, 1, 1. And if PC num found of P cloud is bigger than 0, that means found is plus plus, and we need to find 2 points. So found, if found is smaller than 2, then it doesn't satisfy our requirement, therefore we don't need it. So remove primitive from 0, prim num, remove the points. Apply and accept. So as you can see, all the inside primitives, they have disappeared. So once it is done, we also need to check another important thing. We need to check the roof sides. So object merge, I'm going to bring the roofs. Roof base. Let's call it roof base. Let's actually color all the object import. And in this one, we just need the side. So if I'm not mistaken, we have it marked in our attributes. Yes, side. So it's going to be easy. Just takes a blast. We'll call it sides. And we just say that we want the sides equals 1. Primitive delete not selected. Yes, that is our sides. And what we don't want to do with our sides is we want to measure them by area. And then we want to delete the ones that are too small. So let's say if area is smaller than 5, you delete those. So delete non-selected, delete selected. So if anything in this area is more than 5, it's just going to be deleted. Or we can actually reverse it. Let's reverse it so the 5 is included. Yeah, so if area is 5 or bigger, then it's going to be used. So we will merge that together with our walls. And again, we will have the same routine. We will just take each subnet, and we're going to say that each number for the number of primitives. We're also going to just identify the area. So number of primitives, input path, yes, -1. So let's dive into it. We're going to locate with blast, locate primitive stamp for value 0, delete non-selected. Again, we want to poly expand it because we don't want the cranes to spawn on the very edge. So poly expand inside, and we will make it even bigger, 0.2. And again, we will have the same routine. So actually, let me just copy the one we have in for paddle. So paddle location, let's just copy that for the crane as well. And we'll call it crane location. So in this case, we don't need to keep the bottom because we can just spawn it on all the areas. So delete the keep the bottom. We don't need the connect and sort anymore as well. We will have the switch. We don't need to put it on the ground anymore either. Don't need the connect. So yeah, and in this part, where if this is not a wall, because we also have sides, here we will need to add a switch, because if we're treating the roof, it's a bit different. So here we want to say that if endpoints of locate is equals to 3, and it's going to be a bit different. So let me, well, we don't have a case here, but what you need to do is, let's just copy a clip. We don't need the direction because we're going to use the Y direction. And what we're going to do is just to bring it a bit smaller. I'm going to just cut the top a bit. So in here, connected, so switch, and it's not true. Yes, all correct. 2 switches working fine. And that is what we have. Nice. So once we have the crane's location, let's delete the alt for each. So once we have the crane location, we will just also copy from the paddle the scatter. Crane location, so oops, it's a clip. Scatter, we'll also copy like the whole thing here, because we also need to delete them if they're too close, and for some reason it does not copy for me now. Okay, it does now. So let's bring it here. Scatter, we'll just need a different random seed, so let's bring it something here, and we will say from 0 to let's say 3 or 4. Let's make it 4. Accept. So right now we have only 1. So delete to close, we still need that, and attribute initialize. So the name is not going to be paddle, it's going to be crane, and everything else is the same. So nice. So let's see if it works. Yes, works nicely. So now let's merge crane and paddle together. And yeah, here are paddles and 1 crane. So the last part of the set dressing modules is the boxes and barrels. So let's create a subnet for that as well. Call it box barrel. Let's color it and dive into it. So for the box and barrel, we need to find the area where we can put those boxes and barrels, and those will be under stairs and full and partial supports. So what we need to do now is we need to gather all of them. So we will need to grab an object merge. We will need to take the full support. Yeah, here you are. Come here.
So that is a full support. So let's color it. We also need to grab the stairs. So we need the walkway part. So it's in the stairs and walkway. So let's call it stairs walkway. We will also need just the stair point itself as well. So let's grab that too. So stairs, door point, stair point. So stair point. Yeah, and from the base itself, we will need the doors. So plus, and we will need to type door with non-selected and primitive. So doors. So yeah, for the walkway, I'm sorry, we don't need just the walkway. We need the body. So the stairs body. Oh, sorry, not body, walkway, and there should be the body. Yeah, that's correct. That is the one. So the way we're gonna do it is, let's bring a null, let's collapse subnet, and we will call it get walkway area, and it will be a simple copy. It's gonna be a grid, which is 2 by 1, 2 and 2 in rows, and the center 0.5. And we just simply copy the grid onto the point. That, where we got the walkway area. In a similar fashion, we will get a stairs area. So let's bring a null, collapse it, and we will call it get stairs area. So for this one, we will need to move it a bit and modify its normal. So let's grab attribute wrangle. And we will say that y is 0, position in P is 0, and we also need to normalize its normal. And we need to move it slightly to the cross of its normal, but only by half. So here it is, and we will also copy a grid on it. So copy grid. So 2 by 2, 1 by 1, and 0.5. So it should be in the center. Yes.
The reason for such an area placement is that if you place correctly the stairs, so here they are, and that is our initial stairs point. So to make our area go below the stairs, first of all, we need to move the point so it is on the center of our module, and also we want to put it on the ground, so that is what we do in our wrangle node. And here we can put any area, but if we put a too big area, then our modules cannot fit in this particular part. So that is why we have quite a small compared to our whole module piece of area. So here it is, and that's where the barrels and boxes can spawn.
That's another area, so let's merge them. Oops. Merge them. As well as our full support. Yes, and what we want is just bring them down. So attribute wrangle. It's called put on the ground just by moving every point to 0 in Y. So let's fuse it. And now we just want to scatter the points on those areas. So let's bring for each subnet. It's just for each primitive. It's gonna run poly, expand, and scatter. We also want to make sure that it is removed shared edges. Oh, why is it
broken. Full support. It's broken in such weird pieces. Let's grab the other one. So in support, full support, let's just call it locate full. Yep, I think that will be better. So yeah, fuse, divide, brilliant. So we're gonna poly expand each the inside area, poly expanded by 0.4 to make sure that our barrels and boxes can fit. And then we'll scatter. And we will scatter based on the area, so we will need to bring a measure node. And we will based on the area. And in scatter, not 1000, but a primitive op input path. I'm gonna grab the area attribute. I'm gonna multiply it on a random with a stamp value. For value 0 and multiply it by 2. So apply accept. Yeah, so 5. So what we want to do now is we want to delete the points that do not satisfy to our conditions. What are our conditions? Well, first of all, if they're too close to each other, if they're too close to the door entrance, or if they're too close to the fence entrance. So for that, we will need to bring our fence. However, if you go back to our support system and you go to our not partial, sorry, full support, you remember there we got the in the get pivots we have the fence, and in there we delete a random one. What we want to do here is we want to mark it for deletion, but do not actually delete it. So
since that is an old recording and I actually changed the solution and re-recorded that part, so that is what you saw and followed. That is why the notes look a bit different. But we just want to do absolutely the same thing. Instead of deleting the point, we want to mark it for deletion. So let's do that. For that we will need to create an attribute, create. We will call it attrib for deletion, for del. We will call it delete, and it's a point integer. And yeah, it starts with 0, that's correct. And in our delete random, inside of if statement, we want to set point attribute. So set point attribute, 0 index input. We want to set this delete attribute. For our random number point, we want to set it to 1. So set, that's correct. And now we just want to bring in blast node. And here we just say that if delete is equals to 1, then delete that point. And as you can see, our point just disappeared. So that is it. That's all we want to do here.
when we did that, so let's go back, we can now grab this point that was deleted. So what we want to do now is object merge. We will bring this point all the way from our support, so full support, get pivot, and we want to get the fence one, and we want to delete random. So we have these points now, and we want to blast only the one that was selected as a deleted one. So delete equals 1, and we want to delete non-selected point. Here it is. So we will grab fence entrance, it's called entrance. Yes, and we will mark color it, not the blast, but this. And we will also need our doors, so that's why we have this one here. So all of that will be accounted in our wrangle node. So let's connect the entrance to the second input, and the doors, we don't want just the doors, we want the middle bottom point. So I will just copy that from our support system, I believe, or stairs, it wasn't stairs, yeah. I'll just copy it from our walkway. Bottom line it's called, I think, get bottom midpoints, yeah. Just copy that and bring it all the way back to our set dressing box barrel. Here are points, we will account for them as well. And we will call it delete to close.
So first of all, delete two close to each other. So let's say pcloud pc open 0 p, and let's say it's something like 0.3. So if pc num found of pcloud is bigger than 1, remove the point. Then we want to delete if it is too close to the entrance, to the door. So int pcloud2 pc open, and it was our second input. And I want to make sure that nothing is as close as 1. And in this one, make it bigger, because 1 is always occupied by the point like itself. So here, if, let's just copy this. If pcloud2 is bigger than 0, also remove it. Then, with the entrance, make sure you peak it by 1. Actually 0.5. Because then it's kind of the middle of the entrance. That's what we need. So now we will say delete if it is too close to the fence entrance. So first of all, let's check if there is any fence entrance. So endpoints of first input is bigger than 0. And I will just copy this in here. So if pcloud3 and first index input also 1, yes 1, and pcloud3 apply accept. So none of our points were deleted because the doors are there and the fence entrance is here. All good. Let's just check just in case. What if I say it's free? Apply. Yeah, it works. Good. So 1, apply, accept. So yeah, and then we will initialize the attribute. So attribute initialize. So in here we will add the random rotation. So add random rotation. Again, we will do it like I did with a quaternion and matrix. So rotation random of a point number plus its position. We'll need to fit it between 0 and 1 and 0 and 360, because those are not bound to support anything. They can be any rotation whatsoever. And we want to get a radiance. So we have radiance of that. And we want a quaternion out of this. So quaternion around the y-axis. And the normal is qrotate on that rotation along x-axis. Let's say x-axis, doesn't really matter where we start. So then we need to make the name. It's a box. And the variation, and remember it can be two variation types. So we say 0 plus printf, and here we say d. And here again we will take a random, same as this one, but we will just switch some things around, like say minus. So this is a random. We will also need to fit it between 0 and 1 and 1 and 2, because it's our possible variation numbers. Then we need to round it and convert to an integer, because we don't want to it to print the float. So the type is set dressing, and scale is 1. So apply, accept. So let's see if it works. Plug our boxes into place modules. And yeah, works nicely. So okay. Oh yeah, forgot to merge them together. Or didn't I forget? Sorry, I just forgot to put the flag like display over here. That's why it wasn't properly showing anything. And I still miss the columns. So let me full support. I guess in here, yeah, I'm still on the fence. So merge together. So here we are. And as you can see, we still have a bit of intersection over here. So we might need to poly expand a bit more. It's easily adjusted.
So let's go to the set dressing. Let's go to the box barrel, and we will go to the poly expand and scatter. And we just said we want to poly expand even more. Let's say it's 0.55. Yeah. So that's it for this video, and I'll see you in the next one.
Oh, baby, sad division seas and